So welcome everybody to the 2022 edition of the Optics and Refraction Worldwide Live Stream. We're 12 minutes behind schedule, but that's okay. You're my captive audience. Now let me just make sure. Good, I've got sound share and just a few other. Okay, great. So those of you who watched the trailer, I just want you to know I tried to make that look exciting and scary, but it may be a little bit misleading because it's still just boring me talking for the next multiple hours without a lot of graphics and fancy stuff to get us. At any rate, let's get started. Even though this is not a CME event, just a reminder that I do have some financial interests, which will become apparent over the course of the morning whenever I mention some of these things. And actually just in the next few minutes is where you'll hear most of it. I ran across this book back when I was in my travels. It was Sir Isaac Newton's original treatise on optics back from 1718. And this is really, where you want to go when you want to learn about optics. But for those of you who are just trying to get through an exam coming up or want to be more focused on what we're doing clinically, we also have this book, which you know about and which is one of my financial interests. We're actually working on another edition because you know how quickly the field of optics and refraction changes. So, but we're, around board time, everybody's worried about something to study at the last minute. We only wrote it because I was looking for something to study in my last minute before I was taking the test and couldn't find anything. So decided to write it. And it does okay on Amazon right before, if I time it right before the test. Otherwise it drops down to who knows what. And then I put together some of these other resources for you. One is this web page, which is updated, the Last Minute Optics site. And then if you're already watching this video, you probably know about this YouTube channel, which I created this QR code last night. It's either that or it was a free QR code site. So we'll see where you end up, or I don't know, maybe it's my Ethereum. Maybe it's my Ethereum site, and you can send some Ethereum to that number, to that code. So I was hoping actually to be in the Meltzer Auditorium at Mass Ioneer today, but we just weren't able to make that happen this year. Maybe next time. Instead, I have a fake background of one of our eye lanes at Boston Children's Hospital to keep me company with nobody to laugh at my jokes again, which actually doesn't matter because nobody laughs at my jokes anyway. And so if nobody's here in the room with me, then I can just assume that everybody is laughing, but that and not have to have the reality of nobody laughing when there's a room full of people. So this is just some advice that comes from the Optho Questions people to wait for your last 2 weeks before taking any exam, before looking at this. And in that spirit, I was up late last night trying to remind myself of all the stuff that I'll be telling you about today. So it doesn't seem to get any better after all these years. There are 10 things. We will go through the 10 optics questions that you might want to expect to be seeing. We have this top 10, and let's have a drum roll from the band. Okay, thank you. The number 10 that we would be thinking about are surgically induced refractive errors, and we'll have examples of all these over the course of the day, the evening, wherever you are. Number 9 is contact lens fitting. Number 8 is the U plus D equals V or I decided to start calling it U plus P equals V, which you'll see in a future slide. I forgot to change that one. Number 7, causes of required refractive error. Number 6, accommodation. Number 5, size of a scotoma on a tangent screen. Number 4, Jackson cross cylinder. Number 3, commonly asked question is magnification of a telescope. Number 2 is the vertex distance questions. And the number 1 question that you may be expected to address in a written board exam, more so than an oral, is drumroll and Prentice's rule. Oh, okay. You'll see when we get to it. It'll all make sense over the course of the day. So we have broken this up. I've broken it up into 4 parts. First, we'll talk about the basics, as you see here. Then we'll really dig into refraction, and there's a lot of content in refraction and what's behind refraction. Then we have other optics of note, magnification, the things that you see there. And then finally, we continue to get more clinical, you see, and more practical as we go through the course of the day, is practical matters like prescribing glasses, how instruments work, and just generally managing patients who have optics-related problems. So I will use this placekeeping mechanism borrowed from this ESPN, where you have the what's coming up next at the bottom, and then you can sort of see, so you can decide when you want to take a break and go to the refrigerator, get something to eat if there's a topic that you're not interested in. So this is from the bottom up, you see. So part 1 is coming next, and physical optics will be the next part of part 1. These are the formulas that you think about, or this is why people get worried about optics, because they just see all these formulas and think it's a bunch of formulas and lines on the screen. But really the point of what I'm trying to do today is to break this down into its simpler parts, into the how we spend every day, and what try to help it make sense and show you that these formulas are not your enemies. They're not meant to intimidate. If we break them down one at a time, they can be your friends and help you get through some of these problems that we're asked to solve, and to really help us to a better understanding of how things work. So let's dig into physical optics and the basics. And we will start with talking about properties of light, polarization, and on down this list that you see here. So we'll start with just the properties of light. Oh, yes. One other thing. Here's one thing I stayed up late last night was I thought that in order to keep you awake, I would ask questions, stop and ask questions. And it took me a really long time to decide which emoticon to use next to the questions. But since people seem to not like being asked questions, I thought that the gritted teeth one would be a good one. Anyway, I kind of like that one. That one in the nerd face. I could have done the nerd face one, I guess, but you already got a nerd face here. So the first question is light a wave or a particle? So I'm going to just pause. I don't know how many of you can type in. I've got the little chat thing over to my right. That gives a moment for anyone to think about the question. But of course, this one is a trick question because the answer is no matter which choice you make, you get it right. It's a wave and it's a particle. No one theory explains all the properties of light. There's a wave theory that says that it's a vibration, if you will, a wave of energy. But then there's a particle theory that says that a photon is a bundle of energy of light that goes shooting through space. So either one of those works, and we will use the one that that's most expedient when trying to explain different phenomena. And then there's also a light ray, Now, a light ray has nothing to do with physical optics. That's a construct that we use to figure out where an object is, where an image is, and we'll actually spend most of our time on light rays. This beginning part, we'll talk about waves and particles when trying to explain different properties of light. And so when we think of light as a wave, here we have the full electromagnetic spectrum ranging from very long wavelengths that are as big as a mountain, all the way down to X-rays and gamma rays that are very fine. And the electromagnetic spectrum, within the electromagnetic spectrum, light is just this tiny little sliver. And so there's all this other information out there for us, but we just don't have receptors in our bodies to pick up ultraviolet, infrared. We have artificial sensors. So, but we have the sensors to pick up these this energy. And a light wave, when we think about light as a wave, it has a wave length. That is, it goes from peak to peak. The difference from peak to peak, it has a direction of propagation, which in this case is going from left to right across the screen. And then it has an orientation of electromagnetic. The electromagnetic energy has an orientation. So this particular light wave that I'm showing here has a vertical orientation, but other light waves may have other orientations. So when we talk about polarized light, it has to do with this concept that each of these light waves has an orientation. So if you take an unpolarized light source, which most light in nature is going to be unpolarized, that it's going to have lots of different waves that are at different orientations, horizontal, vertical, oblique, but then you run it through this filter. You run it through a filter that only lets horizontally oriented light waves through, then you have horizontally polarized light. Now, to your eye, that's going to just look like any other light, but it can be manipulated now in ways that you can't manipulate ordinary light. So in this case, I'm sending it through a second horizontal polarizer, and all of the light that made it through the first one is going to get through the second one. But if we now rotate this second polarizer vertically, now none of the horizontal light is going to get through, so all the light is blocked. So this is one way of manipulating polarized light through crossed polarizers. This is a polarizing filter, and you see that the light is either passing through or not passing through, depending on the orientation of the polarizing filter. So when we do polarized microscopy, that involves using crossed polarizers. So there's a microscope, it has a light source. Here you are looking through the microscope, and and I just saw that we had a lot of good answers, so thank you. So we have the light going through here, but now if we put some material in that polarized microscope that has birefringence, that is something that changes the state of polarization of light, then at least some of that horizontally polarized light now has a little bit of vertical orientation to it. So now some of it's going to squeak through that second filter. And so when you are looking through this crossed polarized microscope, you'll see these birefringent materials light up in the dark field. And this is an example of a couple of images that you would see through a polarized microscope. Now, this is back to my financial conflict. I've been working in polarized optics for a few years or decades. It just takes time. But this is a picture of the fovea of the retina taken through crossed polarizers. And so you get a pattern on there. So the idea that Dave Guyton had when I was a fellow was, could you scan the retina with polarized light and figure out foveal fixation, identify foveal fixation remotely, which we did. It worked. We can scan the fovea and get a signature. And so from that, once you have the fovea, you can scan both foveas simultaneously. And so you can detect strabismus, and it turns out amblyopia. So you can get a pass-fail in this device. Here's what the device is that we built. We're now selling it to pediatricians as a vision screener. You come in, they look inside, and now you have you have bilateral simultaneous foveal fixation, then you get a pass. So it's a very highly sensitive for detecting amblyopia. And that's not my day job, but something that I've been working on. Oh, we have a question to wake you up. What is coherent light? Now, I don't know how much of a delay there is on the chat for me to look, but everybody who types something in kind of, so what is coherent light? I can't remember, but once I see the diagram, I'll be able to answer it. So even if you don't type in anything, I'm just giving you a minute to think about what is coherent light. Well, let's just go to, oh, and what happens when coherent light waves interact? Because coherent light interacts in a certain way. Okay. So, so this is, there's a question there, but I'm going to skip that question because I don't want to talk any more about blink than I already have. But so coherent light is light where all the peaks and valleys are aligned with each other. So the way that before the days of lasers, the way that they made coherent light was you would pass light through a slit, and then this is one light source. So all these, since it's just one source, all the waves are aligned, but then you pass it through a second screen that has two slits in it. And this acts as two different light sources where all the peaks and valleys are going to be lined up. So that is so coherent light waves are the same wavelength and the same frequency, but they also are all aligned in terms of when their peaks and valleys. Now, when coherent light waves interact, the answer to the second question, what happens when they interact? You get interference. So in this case, the peak of this light, where the peak of this light matches the peak of this source, then you get a maximum, like so, and where the peak from this source matches the valley from this source, you get a minimum, and they alternate across the screen. So I have a short clip from a YouTube video. I find if I make the clip too long, then they demonetize.
Then we start getting an interesting pattern. This with peaks and troughs with troughs, the amplitude.
So you see how the peaks and the troughs line up there, and you get these interference patterns through. So that happens in water as well as with light. It's just can sometimes be easier to see some of these things with water. So you can have constructive interference. You can have where you get a maximum, destructive interference where you get a minimum. There used to be a potential acuity test where if you would put two beams of coherent light through the lens and onto the retina, because then the lens doesn't have to form the image. The image doesn't form until the light has made it through the cloudy lens and gotten to the retina. So you can ask patients whether they see a grid pattern. Since now everybody just operates on cataracts, as soon as you can tell there's a cataract, then there's a little less use for that. So one place that interference is used is in anti-reflection coating. So when light passes through any substance, there's going to be some of that light is going to be reflected back. So you're going to get reflections. But you can use interference here, destructive interference, by putting a thin film on the surface of the glass, a quarter wavelength thick, and that way you'll get some light bouncing back still from that source, but then you have another bit of light bouncing back from the surface of the film. And so those two beams that are reflected, you see, cancel each other out. And so you get less light coming back and more light going through. So that's the basics of an anti-reflection coating. And you'll see how it can prevent blindness in this little clip from that I found. Why get anti-glare coating on your glasses?
That is the difference. The top pair will protect you from light shining in behind you and blinding you, and the bottom pair does not. Trust me, these are my actual glasses, and I can attest that I should have got the bottom pair with the coating.
So there is the difference between anti-reflection and no anti-reflection coating. Now, OCT, optical coherence tomography, is something else that uses this concept of interference. You have a source that bounces light off of the eye, and then comes back to a detector. But then you have then it also bounces off a mirror, and so the light that goes through the parts of the eye gets slowed down different amounts by different substances within the retina, and so that creates an interference pattern, and we can show that in this. This is sort of an example of a interferometer or something that's using interference. So the light is going to two places. You saw it's going to the left and straight ahead. Now it's bouncing back, and then it's bouncing back from the other one too. And now we're going to get interference here. And depending on the distance that each of these pass, you can either get destructive interference. We're going to zoom in, or if you make the path a little longer or shorter, you get either constructive or destructive interference. And that will create either more or less light. So that's the basis of optical coherence tomography, is interference or coherence. So, question, it's time to wake you up again. Why does actually somebody used the word phase. I didn't even use the word phase, but that's correct. The coherent light, all of them are in phase. So why does a pinhole occluder? Why does a pinhole occluder improve vision? So a pinhole occluder, we know, improves vision. So why would a small pupil, like a pinhole-sized pupil, reduce vision if a pinhole occluder improves vision? Like they're both should be doing the same thing, right? Let's give you a second to think about that. So a pinhole occluder helps you see better, but a pinpoint pupil makes you see worse. Think about that. Well, and then there's a little bit of lag for me to see the answers, so I don't get to see your answers until I start talking again. Again, your answers are over there. That's what I'm looking at. Well, let's talk about diffraction, and then we can understand. So here is 3 beams of light that have passed through different size pinholes. And as an ophthalmologist who uses pinhole occluders, you're probably thinking that the bottom one went through the smallest pinhole, but actually it's the top 3 that went through the smallest pinhole, and that's because of diffraction. So when light passes through a very small aperture, you get spreading of the rays of light as they pass through that aperture. And so a very small pupil like this, like is shown here, is going to cause diffraction or spreading of light. Now the pinhole itself, when a pinhole is larger, it shrinks the size of the blur circle, but you get to a point of diminishing returns as the pinhole gets to become too small. Now you get diffraction taking over. So there's an optimal size for a pinhole occluder. Here's a water simulation that shows the effects of diffraction that I found. The video, for some, I can't seem to get it to stop. It lags oddly when it first starts, but eventually it catches up. So give it a chance. Here we go.
Well, you might be surprised to learn that a narrower aperture leads to more spreading out of the wave, more diffraction. If instead I make the aperture wider, then after it's settled down, you can see that the wave becomes less spread out. The diffraction is less pronounced. And if I were to make the aperture very wide indeed, then there'd be hardly any diffraction.
I just left that last part in there because it's just awesome to see that he's so is definitely into this. So you see, the smaller the aperture, the wider the spread. So that is diffraction. Scattering is a different phenomenon, not the same as diffraction. Scattering is what happens to light when it bounces off of particles that are of similar wavelength. So we have a little explanatory video here.
You'll notice immediately that the blue photon is moving around a lot more in the same amount of space, and thus is scattered more. Every time one of those atmospheric particles glows, that's supposed to represent scattering. In real life, blue light is actually scattered by a factor of 6 times more.
Okay, so all light is scattered. The light is bouncing off air molecules, but blue light, being higher energy, higher frequency, bounces off of more particles and so gets scattered more. And as a result, that's why we see, when we look up to the sky, some of the light from the sun makes it directly to us without much scattering, but the blue light scatters everywhere. If it wasn't for scattering, then the sky would be black because all the light from the sun would just head straight toward us. But instead, it bounces off the particles in atmosphere and indirectly finds its way back to our eyes. When the particles are large enough and dense enough, then all the light is scattered, and that's what happens with clouds. Here's another example of scattering, asteroid hyalosis. We've all seen patients with asteroid hyalosis. What's amazing is you can see patients who have this, who have completely normal vision and have no complaints, even about floaters, or their visual acuity is fine. And the reason for that is also because of the way it has to do with scattering. But in this case, when a patient has asteroid hyalosis, when they're looking at a letter, say out in the world, that letter it does hit these particles, but the particles just cast tiny and short little shadows that don't make it to the retina. So enough light gets through to be able to see the letter E in this case. But when you put on your indirect ophthalmoscope hat with its bright light source, then the light that's coming off of your indirect is going to bounce off of those particles and bounce back into your eyes, so you get the scatter back into your own eyes and have trouble seeing, but the patients can see just fine. So we have another question. What is the refractive index? And what does it translate to physically? So I'm just going to give you a chance to think about that. What is refractive index? And you can feel free to type in answers or just think about it in your own head. What is the refractive index? I don't remember, so I'm going to have to look at my next slide and see what that is. What does it translate to physically? So the refractive index is translates physically into speed of light, in how speed of light changes as it goes from one substance to another. So when, for example, if we have here, imagine that most of the slide is a vacuum, but that this little box here is a piece of plastic, clear plastic. So when light is going to be going at the speed of light in a vacuum, once it enters this plastic material, here it's going to slow down. And so the ratio of the speed of light in this slowed down material on the bottom, the speed of light in a vacuum on top, is refractive index. Now, light can't go any faster than it goes in a vacuum. And so the refractive index is always going to be higher than 1. It's always going to slow down in the other material. And so the refractive index of air is pretty much 1. So if we back up here, so the speed of light in a vacuum, speed of light in air, about the same. The water goes more slow. I mean, the light slows down by, say, 33% in water, 37% in cornea, even slower in the lens of the human eye, slower in plastic lenses, slower in crown glass. And then there are high index materials. For example, there are high index glass materials where the light is 80% slower in this glass than it is in a vacuum. So that is what a refractive index is. And it's not especially interesting to see what happens that light, when it's perpendicular, or we call it normal to the interface here, it's going to slow down and enter the glass, and then it's going to speed up again when it leaves the glass. And nothing much very interesting happens when it's perpendicular or normal to the surface. But things get interesting when the light enters away from the normal to the interface, because what happens is that now the light gets deflected towards the normal to the interface. When you go from low to high refractive index, the light changes direction into the slower material, so towards the normal to the interface. And if you increase, so here we are going in at one angle, and we go towards the normal to the interface. If you turn the light around and go the opposite direction, now we're going to go away from the normal to the interface. When you go from high to low refractive index, it's away from the normal to the interface. So towards the normal this way, away that way. And what it really means is the light is following the same path. It doesn't matter which direction it goes, it's going to be following the same path. Now, if we, when we're going away from the normal to the interface, though, one other interesting thing happens, and that is that if we increase this angle of incidence and make it more oblique, so let's make it more oblique, then you're going to be leaving even more away from the normal. And if you make it even more oblique, you're going to be even more away from the normal, to the point where eventually the light is going to be just humming along parallel. The light that's exiting is going to go parallel to the interface itself. That angle we call the critical angle, and you can calculate it using Snell's law, putting in, we're not going to calculate it here, but it's for ordinary glass, it's about 41 degrees. And once you exceed that critical angle, then the light cannot escape from the higher refractive index material anymore. This is called total internal reflection. And total internal reflection is very efficient. It keeps more than 99.999% of the photons inside of this material. They cannot escape when the angle of incidence is greater than the critical angle. So we can use that in this, I think this is the engineer guy who made this, this video, and he's going to pour the laser light into a bucket using critical angle, using total internal reflection to keep the light captured within this high refractive index substance.
That's wonderful. The light follows the liquid flow all the way to the bucket. Amazing. For this propylene glycol and air system, as long as a beam hits the surface at an angle greater than 44.35 degrees, measured from the normal, it will propagate down the stream via total internal reflection.
So there you go. He's very enthusiastic about that. But it is kind of neat. Pour light into a bucket. So the other place that we don't generally pour light into buckets in our eye clinic, but we do try to perform gonioscopy. And when we perform gonioscopy, we need this extra layer, because you can't just see into the angle structures of the eye by shining your flashlight in obliquely. There's no way to see in there. And the reason is, let's follow the light from the angle to your eye, or trying to get to your eye. So we start here, and then we go this way, but then it's greater than the critical angle where the So the light goes through the aqueous, through the cornea, through the tears, but then it hits this tear-air interface, and the tear-air interface goes from high to low refractive index at greater than the critical angle, so all the light stays in. So you can't see anything. You just can't see it. So what we can do, though, to fix it is we change the tear-air interface to a tear Goniosol plastic interface into this device, the gonioscopic lens. And then once it's in here, you made it out of the cornea. Now you have one more mirror, change the direction of light so that now when you go from high to low refractive index, you're no longer at greater than the critical angle. So the light passes on through and you can see what happens. The whole concept of gonioscopy was discovered in a patient who had an abnormally steep cornea from pellucid degeneration of the cornea. And it got me to thinking, so here you can't see angle structures. You could maybe convince yourself you think you do, but you're only just seeing the edge of the iris. There's no iris, there's no angle structures. But I was wondering, my cat, well, this was our late cat Buttons, but she's got such a steep cornea. I thought maybe we can see the angle in her cornea. So, but she wasn't really very interested in letting us actually try to look and do this experiment. And so after some effort, we just finally kind of gave up. Although Retina was saying, oh wait, is there angle structures there? Oh, maybe not. I don't know. So no, I can't tell you for sure. But we do have these lenses, the Kepi lens that we use in pediatric ophthalmology. It's all it's doing. It doesn't. It's not like the. It's not like the Goldmann lens that just changes the angle. The Kepi doesn't have a mirror in it. It just has a super steep surface so that the light can escape without having to be greater than the critical angle. So that is, so those are the basics of physical optics. And now we're going to move on to talk about vergence. So we'll talk about the definition of vergence, the lens formula, real and virtual images, and the refracting power of a spherical surface. So when we talk about light today, we're talking about light as rays. So here's a ray of light that's going from left to right. And generally speaking, unless I say otherwise, we will assume that the light is traveling from left to right on our screen. And when that happens, the rays of light in a beam of light can either be converging. When that happens, we call it plus vergence. They can be diverging. And when that happens, we call it minus vergence. And then they can be parallel. And when the rays of light are parallel, we say that they have zero vergence. So what exactly is a diopter? I'm just going to stop and think about that. It's like we use diopters all the time, but what is a diopter? Give me a chance to have a sip of green tea while you think about what is a diopter. I'm just looking for answers. So a diopter is a way of describing the vergence of light. And so in particular, it's the reciprocal of the distance in meters to the point where the light rays would intersect. And so the point where light rays intersect, that's either where your object is located or where the image is formed. So that point of intersection is critical to the formation of images. The light rays intersect. And so the distance from that point of intersection is the vergence, and the unit is diopters. And what the diagram here is showing you is that it's not about the angle, because you can draw this angle however you want. What matters is where's the point of intersection, and how far away are you from it. In this case, you're 1 meter away, and so the reciprocal of 1 meter is 1, and it's 1 diopter. As we go from left to right here, the rays of light are diverging, so that's -1 diopter of divergence. If we have a light source off to the left that's creating converging light, like so, the rays of light are going to converge to form an image at this point, but then they continue past the image and begin to diverge again. So the divergence, here we are 1 meter away, we just said, if we're 1 meter away from the point of intersection, and this time it's converging light, then it's going to be +1 diopter of divergence. If we're 1/2 meter away, then it's going to be +2 diopters. 1/4 meter away, it's going to be +4. 1/10 of a meter away, it's going to be 10 diopters. 1/millionth of a meter away, it's going to be 1,000,000 diopters of divergence. And then finally you hit infinity, infinite diopters of divergence at the point of intersection where the object or image is located. Then you go from infinity and beyond to -infinity, but then you come back in the other direction. Now we're 1/4 meter away from the point of intersection. So it's -4 diopters, -2 diopters, -1 diopter, and off we go. So this diopters are, in a sense, telling you a distance, but the distance is it's the reciprocal of the distance. So lens powers then are actually, those diopters of lens power are telling you how much they change the divergence of light. So if you have parallel rays of light coming into this lens on the top, it's going to add plus divergence, so it's going to cause the light to converge. Whereas if you have parallel rays of light coming into a minus lens, it's going to diverge the light, so it's going to add negative divergence or minus divergence and diverge the light. So a plus lens adds plus divergence, a minus lens adds minus divergence. So this leads us to the basic lens formula, which says that the divergence of light entering the lens plus the divergence added by the lens equals the divergence leaving the lens. And that formula is U plus P equals V. So this is a big deal for me. Those of you who've followed me all the way back to the 2010 lecture, which I recommend the 2010 lecture, because after I did that one online, I had to give up on a bunch of jokes that I put in that one. So, these have to be all new jokes. So you only can get the old jokes by going back to the 2010 lecture. But anyway, I've always said U plus D equals V, because that's the way Dave Guyton said it. And but really D is diopters. So would you really want to name your variable the same as your units? And some of the books, including the basic science study course, uses P. So after discussion with Mike Wan, who also gives lectures on optics, I've come to the conclusion that we'll use P. So a big moment in my life, going from D to P, and sort of, maybe separating from my mentor, going a different direction from Dave Guyton. So hoping I don't get disowned by him. So U plus P equals V. The divergence plus the entering plus the divergence add equals the divergence leaving. So we'll do an example. We have an object. It's 2 meters away from a +2 diopter lens. Where is the image? Well, we should be able to figure that out. We need to know what is the divergence entering the lens. Well, the divergence entering the lens must be the distance from the object. So we're 2 meters away from the object. We see it's diverging light, because any light that's emerging from a natural object in the world is going to be divergent. So 1 divided by 2 meters is 0.5 diopters, negative 0.5, and then U plus P equals V, negative 0.5 plus 2 equals positive 1.5. So the divergence leaving the lens is positive 1.5. So where is it, to the right or to the left of the lens? Well, it's plus divergence leaving the lens, so it must be converging light. So therefore, it's somewhere to the right of the lens. How far away is it? Well, we take a reciprocal. 1 over 1.5 diopters is 0.67 meters. And so the image is 0.67 meters to the right of the lens, or 2.67 meters away from the object in this one lens system. And so this brings us to the first rule of optics. So what is the first rule of optics? Those of you who've seen this before know my first rule of optics is, when in doubt, take a reciprocal. So if we just back it up here for a second, here you are, you've got two numbers, you've got an object, and you're blanking. You're like, oh my God, I studied this 2 weeks and 1 day ago. I've completely forgotten how to do these. So you know you've got to take a reciprocal of something. Now, fortunately, in this case, both of the numbers are 2. So it's 1 over 2. So something is 0.5. And maybe the act of getting to the number 0.5 will say, 0.5, vergence. That's the vergence entering the lens. And then you're on your way. So when in doubt, take a reciprocal. That's just some like PowerPoint man that I found deep in the belly of my PowerPoints. So here is a table of reciprocals, and yeah, probably ought to memorize this the night before the test. I mean, a lot of them are like 1 over 1. I'm hoping most of us can get that one. 1 over 2, pretty good there. 1 over 3. 1 over 4, but some of them are a little more obscure. And I mean, I don't know if you're going to be doing 1 over 16, but the bold ones you certainly want to know. And then 1 over 1.5, I guess maybe I should add 1 over 1.5. So that is just something for you to consider. Now, we said that when two rays of light intersect, that creates an object or an image. And when we're looking at any lens system, we have the object space and the image space. So this matters when we're talking about real and virtual images. You see, this is where we are in our journey. So the incoming rays are always, that is the object rays, they're always on the left of the lens. The outgoing rays, or the image rays, they're always to the right of the lens. So that never changes. The object rays are always on the left. The image rays are always on the right. So the object. But the object itself and the image itself is not always on the same side as the rays that define it. So I have a question here for you, because we got to stop, because this is Zoom and it's very easy to start wandering, have your mind wandering. Here's an object and here's an image. It's just like that one I just showed you, object. So is this a real object or a virtual object? How about that image? Is it real or virtual? How about this one? Is that a real object or virtual? It's the same as this one. So whatever it was, it's the same. This image looks a little different though. So this is so these are real, that's a real object and a real image, because the object is in the same side of the lens as the rays that define it. I just accidentally figured out how to zoom in on my PowerPoint. That's exciting. I also just accidentally converted the laser pointer to permanent. But anyway, the image is on the same side as the rays that define it. But here, look at this. This is an object. The light's passing through a minus lens, so it's diverging rays of light. So where does the image form? Well, we can go all the way to the right, but the rays of light are just continuing to diverge here. They're never going to come back. So we have to create imaginary extensions of the rays of light back to a point of intersection on the opposite side of the lens. And so the image is on the opposite side of the rays that define it. So that is a virtual image. And now I can't get out of my laser pointer, so I can't change my slide. I'll figure it out, don't worry. Oh, another question. Is there such a thing as a virtual object? Because and the reason I ask is, like, how would you have an object if the rays of light are always diverging from an object, then how could there be such a thing as a virtual object? I don't know how I got my laser pointer on. Pointer. No. All right. So, is there such a thing as a virtual object? Why, yes. If so, how can one be created? Well, what you need is another lens system somewhere hidden. It's somewhere off screen, but there was another lens over here that created these converging object rays, which then go into a lens and create an image. But we have to create imaginary extensions of the rays of light to a point of intersection on the opposite side of the lens. So it's a virtual object on the opposite side of the rays that define it. It's so funny. I was trying so hard this morning to figure out how to permanently turn the laser pointer on, and now I can't. Let's see if. All right, we're getting some answers. At least one of us is awake. Thank you, Blabberoid. So we have next the refracting power of a spherical surface. So that is, how is it, and this is kind of neat when you think about it, like how is it that a lens is actually changing the divergence of light? And it all goes back to this idea that light is deflected towards the normal to the interface when you go from high to low refractive index, because imagine a whole beam of light coming in here. Well, this one on the top is going to be deflected towards the normal, so this one's going to be deflected down, but the one on the bottom is going to be deflected towards the normal, so it's going to be deflected up. And so that spherical surface is going to, in this case, add plus divergence because of its shape being the way it is. And the strength of the change in angle of the light has to do with the difference in refractive index across that surface, because the more slowing you have of the light as it transitions across that interface, the more bending of light you're going to get. And so it's n prime is the refractive index on the left. In this case, we're in air most likely, so it's 1. And then n is the refractive index of whatever this material is. So n prime minus n is the difference in refractive index. The other thing that is going to make the light bend more is the more curvature you have of this lens, the more the light is going to bend as it passes through, because it's going to be more oblique to the interface. So you're going to get more bending. So R is also important. And so and that's all you need to figure out how strong this refractive surface is. The power of the refractive index, or the power of the surface in diopters is, oh, I guess I need to make that into a P2. Oh no, I got to change more slides. The power is n prime minus n over r, and that's going to tell you the power of this refractive spherical surface. So I have a question. Why is our vision so blurry when we open our eyes underwater? Like, it's really blurry. It's really hard to see. Let's give you a minute to think about that while I continue to try to understand how I permanently turn my laser pointer on. Maybe I did Control Shift click. No. I did Windows key click. No, wasn't that. All right, have you thought about it? Good. So now, nobody typed any answers in though. So we'll get to the answer here. The refracting power of the surface of the cornea is, we can calculate it by doing that same calculation, n prime minus n over r, because we know that the refractive index of cornea is 1.37. We know the refractive index of air is 1, and we know the radius of curvature of the cornea is around 0.007 meters, or 7 millimeter radius of curvature. So we just plug in those numbers, and the power of the cornea is 1.37 minus 1 is 0.37 divided by 0.007, or 52.9 diopters. So the front surface of the cornea has a power of 52.9 diopters. Now, how do we know if that's plus or minus power? Well, we know intuitively it's plus power, but how do we know? And then there's a back surface here too. And how do we know what the power of that? How do we know if that's plus or minus power? Well, they both look like plus power, right? Or are they? Or is that a minus power? Huh. I don't know. So what we do is we draw a box around it, and then we color in the side that has the higher refractive index. And then we can look at the colored in part, and envision that as a lens. So to determine plus or minus power, here's a refractive interface. We draw a box around it. And then if n prime is higher, then you see it looks like a minus lens. Whereas if n was higher and we colored in the n side, then it would look like a plus lens. So for the front surface of the cornea, I'll just back it up here. We know that it's just 1 in air, but it's, so whatever we just said, 1.4 here. So we would color in this. So the front surface of the cornea is plus power. But the back surface of the cornea, the refractive index of cornea is 1.37. Sorry, I said 1.4 earlier. It's 1.37. Refractive index of aqueous is 1.33. So the cornea is slightly more refractive index than aqueous. So we color in that side. And so the back surface of the cornea has minus power. How much power? We'll plug it into the formula again. Oh, and by the way, it's enough power to not be ignored. Maybe estimating the total corneal power is from ophthalmology times, so academic treatise. The posterior corneal curvature has a greater effect on total corneal power in keratoconus eyes than previously realized. So it matters. But it's not all that much. It's 1.3. So now n prime minus n, instead of 1.37 minus 1, is 1.37 minus 1.33. And so that only gives us 5.7 diopters. And we just figured out that it's negative power. So that 52.7, which I know sounded kind of funny to you anyway, because you're thinking, I thought the cornea was more like 45 diopters. Well, now we're getting a little closer because we're taking the 52.7 minus the 5.7, and that's getting us into that closer to that 45 diopter range. And it's just you tweak the radius of curvature by a little bit, and you can get it right to 45. So back to our question: why is it so hard to see underwater? Well, now, instead of the front surface of the cornea, instead of being refractive index of cornea 1.37 minus air 1.00, Now it's refractive index of cornea 1.37 minus water 1.33. So the front surface of the cornea, when you open your eyes underwater, its refractive index has gone from 52 down to plus 5.7. And then you subtract the 5.7 off the back surface of the cornea, and it's as if you're halfway through a corneal transplant. It's basically when you open your eyes underwater, your cornea has optically been removed from your eye, and all you've got is the 15 diopters in your lens to focus the light. So now when we put those goggles on underwater, and now we can see again, is that because they're 50 diopter power in there? No, because they work above water too. So all they're doing is they're restoring that air cornea interface, that all important air cornea interface, so that we get our 52 diopters back on the front surface of our cornea. Oh, it's time for a question. Just in the nick of time. I want you to try to answer these questions because it's really important to keep you awake. If the power of an intraocular lens is marked as plus 20 diopters, what would be the power of lens if measured in air? So to think of this, I got to pause and just have you think about it for a minute. This actually requires some calculations, so I won't make you think about it too long. I want you to at least think about the concept. It's like, so it's going to be different in water than in air because the refractive index is different. Another way to visualize it is imagine that you had a lens made of PMMA plastic and you put it into a vat, a square. Now you have a square like vat, and it's got clear sides, and the vat is full of liquid PMMA plastic. And now you have a really strong lens, and you put it into liquid PMMA plastic. Well, now it's like you got no lens at all, right? Because it's just a bunch of PMMA. There's no refractive. The n prime minus n equals 0. I could even tell you that I have an air lens here. See my air lens? Nice. Hold it like that. See, air. It's an air lens, and it's very strong when it's underwater. But up here in the air, it has no power because there's no refractive interface. All right. See, there's nobody. I can't see the audience, so I can't see if you're bored, and then I know it's time to like move on and stop digressing. But that's why we have 6 hours set aside for 4 hours of content to give me 2 hours to digress. So here is how we do this, is we use that same formula. So we want to know, okay, well, we had the power in air, we want to know the power in water, or vice versa. So we use that same D equals N prime minus N over R, but then we create it into a ratio because you no longer need the R, because the R isn't going to change if it's in the air. If it's in the water, the radius isn't going to change. So you wouldn't expect that to be in your formula. You just make a ratio. Power of air equals N prime IOL minus N of air. Power in aqueous is the refractive index of the IOL minus the refractive index in aqueous. So it's just the difference in, it's the ratio of the difference in refractive indices. And so power of in air, we know NIOL is 1.49, that's plastic. We know air is 1. We know aqueous is 1.33. So you plug in all those numbers, and then we know that the power of the lens in aqueous, it's labeled as plus 20, so we know it's plus 20. So all we're missing is the power in air. So then you do 1.49 minus 1 is 0.49. That's whatever that is. Now you cross multiply 20 times that number equals D air times that, and then you divide it out. So doing the arithmetic, you get the power in air is 61 diopters, which is pretty, it's a pretty impressive change in power by doing that immersion in fluid. It's 3 times stronger in air than it is in aqueous. So that's why those lenses are so expensive. You're buying a 60 diopter lens just to get a 20 diopter lens into the eye. probably not the only reason. So where are we? We're still in basics. We still have 3 whole other parts to go. But it looks like we're in the last part of basics where we talk about lenses and ray tracing. So we'll talk about focal points, focal length, central ray, thick lens, model eye, all that good stuff. So if anyone knows how I managed to permanently turn this on and then can't turn it off, you can put that in the chat. I'll figure it out eventually. Maybe. So at least I got the live stream going. So focal points. I thought I had a question about focal points. I do. Question. What is a focal point? I'm not just dishing it out to you today. I'm making you think first. What is a focal point? I mean, if I just told you, you'd probably just forget immediately. Now you won't forget for 2 weeks. So a focal point is, wait for it. Oh, wait, we got another question. How does a primary focal point differ from a secondary focal point? Well, I haven't figured out what a focal point is yet, so maybe you don't know, but we'll get there. I got to look at my slide too, because I already forgot the answer from last night. So a focal point is the point at which you would place an object so that parallel rays of light emerge. See if anybody typed that in before I thought of it. No, not yet. A focal point is the place at which you would place an object so that parallel rays of light would emerge from the lens. So for a plus lens, if you put it, say, here, then you have parallel rays of light emerging. For a minus lens, you need to put a virtual object over here to the right. So you have converging rays coming in, and then they come out. But so that's the primary focal point. So what's the secondary focal point? That was the other half of my question. Well, this one you can probably figure out, even if you just accidentally tuned into this lecture. Secondary focal point is the point at which you would place an object. Oh, I don't have that answer yet. Well, we'll skip ahead. Hang on. That where parallel rays of light are brought into focus by a lens. So secondary focal point is, for a plus lens, easy to intuit. It's on the right side of the lens. For a minus lens, you're going to have diverging rays of light. So the secondary focal point is going to be to the left of the lens, of virtual secondary focal point. Now, lenses don't just have focal points, as you saw in my sneak preview slide. You can have a whole focal plane of a lens where any place in this plane that parallel rays of light are going to emerge. And so, so the retina would be, it's not exactly a plane, but it's going to be, for the most part, in the secondary. It's going to be in a focal plane for the optical system of the eye. So that's primary and secondary focal points. So the secondary focal point, if you wanted to burn leaves with a magnifying glass, you would hold that lens at the parallel rays of light coming from the sun. The rays of light would be focused into a point. You'd place the leaf at the secondary focal point, and it would catch on fire from all the heat from the sun. So the focal length is the reciprocal of the dioptric power of the lens in meters. So there's our formula, F equals 1 over D. I think we can all, even if we're not math whizzes, can handle this formula, that the focal length is the reciprocal of the power of the lens in diopters. So even if that doesn't still feel intuitive, let's look at some examples. A 20 diopter lens, like the one we use for indirect ophthalmoscopy, it has a focal length of 50 millimeters or 5 centimeters, because it's 1 divided by 20. Oh, there's a reciprocal again, is 0.05 meters or 15 millimeters. A 3 diopter lens has focal length of 330 millimeters, etc. And so when you hear about, your camera has a 50 millimeter lens, then it is actually a 20 diopter lens. And so when you talk to physics people or engineers about lenses, they don't know what diopters are. They only know lenses by their focal length. So, well, they probably do know what they are, but they just don't admit to it. At least the engineers I talk to in our company, they're all optics gurus, so they don't want to mess around with diopters. Oh, a question. For any object and lens combination, how do we figure out if the image is upright or inverted? I can't resist but look over at the chat. I appreciate those of you who are trying to tap in answers, going out on a limb. So for any object and lens combination, how do we figure out if it's upright or inverted? Well, we would need to draw a central ray. So first, we would have to create an extra axial extension of this object. So you have to just assume that the object is not has some extra axial extension, and then the central ray goes from the tip of the object through the center of the lens, and that's the central ray. Here's another example of a central ray. Oh, and so then, sorry, there's a central ray. Then you do U plus D equals V, and you figure out where the image is, and then you draw the image from the where it's located up to the central ray, because the tip of the image is going to correspond with the tip of the object. Both have to fall on the central ray. So in this case, you know that the image is inverted. Whereas in this case, we draw our central ray, we do U plus D equals V, and it turns out that there's a virtual image somewhere to the left of this lens. And so we draw our lineup and we see that this image is upright, and you can also see that it's magnified. So that's all thanks to the central ray. So the corresponding points of the object in the image must always fall on the central ray. So we've got, so here's our object, here's our lens, and if it's a plus or minus lens, it's going to put the images one way or another. Depending on the power, you're either going to have upright magnified, upright minified, inverted minified, or inverted magnified. So actually you can figure out where images are and objects, without doing any U plus P equals V. You can do the whole thing with ray tracing. So you get your graph paper out and you draw 3 rays. You draw one through the primary focal point of the lens to the lens. You draw one to the lens and then through the secondary focal point, and then you draw the central ray, and they all converge where the image is located. So that's another way to do it, but it's kind of hard to do that when you're taking an exam. So my preference is to use the Vergence formula, U plus P equals V, and then use your central ray to figure out if the image is upright, inverted. And then we'll talk about magnification as well, but usually if you draw it on the central ray, you can figure out if it's magnified also. So so not all lenses are ideal thin lenses that have a single, that have light passing through a single point and moving on. Real lenses in real life have a bit of thickness. And so it gets a little bit more complicated in how we calculate it. So, instead of having a single point, you have 2 nodal points, and the light goes from the tip of the object into the first nodal point, then it jumps to the second nodal point and continues on to the in the same direction. And then instead of calculating the distance from the object to the center of the lens, you calculate from the object to the first principal plane, and then from the second principal plane to the image. So, so refraction occurs at the principal planes, which are separated in space, and the central ray jumps between the two nodal points. And there's one other thing that's not exactly about a thick lens, but it's a question for you. What happens to these nodal points if one side of the lens is immersed in fluid? That is, it's the less general case of when you have different refractive indices on the opposite side of a lens. Like, what unusual thing happens? Just give you a minute to think about that. There's not a whole lot of unusual things that could happen. So what happens is that the nodal points get pulled in. The nodal points get pulled into the medium with the higher refractive index. And so I don't know exactly how or why that happens, but it does. Now the principal planes don't move, but the nodal points do move. And so, you just got to accept that that's the reality. And so that will affect your calculations. Now, it might seem like we're going a little off course here. Like, this isn't a tangent. We're headed towards something, because what we're trying to head toward is understanding how the optics of the human eye. And we need these bits of information to understand how the human eye works. So that's what Gullstrand figured out. He did it for us. He won a Nobel Prize for this work. I did used to say that he was the only ophthalmologist to win a Nobel Prize. I've been corrected on that. There is another ophthalmologist who won a Nobel Prize, but it wasn't for an ophthalmological topic. And I'll just leave it at that. It's going to be in the third edition. The full explanation will be in the third edition of Last Minute Optics, which is currently in production, which I would have worked on last night, except I was up so late working on this lecture for all 51 of us. So weird, when I did it 2 years ago, there were like 500 people here. So I don't know what I guess my promotional somehow didn't get it out on the web quite the same way, but that's all right. People will watch later, maybe. So Gullstrand worked out the optics. So you see, it's like a thick lens. There's aqueous on one side, there's air on the other. So the nodal points have been pulled in. It's got two principal planes, two nodal points, and then it's got a primary focal point and a secondary focal point, and the secondary focal point just happens to land on the retina, which is good because that means that this eye is in focus. But we're not going to go into all the details of this because there's just too many numbers after the decimal point. So, and what we can go with instead is the reduced schematic eye. So the reduced schematic eye is a little simpler. So you see that instead of two principal planes, we've got one principal plane. Because they're so close together, we can say that they're one. And we can also say it's probably right on the cornea and not behind the cornea. And then instead of two nodal points, we'll say there's just one nodal point because they're very close together. But you can't get away with saying the nodal point is like also on the cornea. The nodal point is definitely pulled back into the eye, and it's 5.5 millimeters away. And the power of the lens, the eye, instead of saying it's 58.6, we'll say it's 60 diopters. Now 1/60 is 0.17 because you memorized that table of reciprocals, 1/6. 1/60, that's what gives us the 17 millimeters from the principal plane from the primary focal point to the principal plane. And then 60 also gives us 17 millimeters from the nodal point to the secondary focal point. And then that 5.5 is in the middle. The index of refraction of the eye, we think of it as just a uniform surface of 1.33. So there we are with the reduced schematic eye. This is the one we use when we're trying to answer questions about how the eye works. So, which we'll get to, but I just want to remind you of a little bit of trigonometry, is that when two triangles have shared angles, such as is shown here, then you can use the concept of similar triangles to figure out the missing leg if you only know 3 of the 4 legs. So A divided by B equals X divided by Y. That's similar triangles, because we'll need that for the next question. So we have a question. What is the diameter of the blind spot when projected 2 meters from the eye? Well, geez, there's no reciprocal to take here. I think we don't have enough information. So what we need to know is, how big is the optic disc? Well, what we also need to know, so we're going to assume it's 1.7 millimeters. And then what we also need to know is, what's the distance from the nodal point to the retina? Because we're going to draw a central ray from the tip of the object through the nodal point and off into space. We know that the nodal point is 17 millimeters from the retina. We know the optic disc is about 1.7 millimeters high. We could say 1.5, but it makes the math easier if we say 1.7. Then we draw our central ray from the tip of the object through the nodal point and off into space. Now we know that it's there was a number here, 2 meters from the eye. Luckily, we didn't take a reciprocal of that. And so this is going to be 2 meters from the front of the eye to the that distance to the front of the eye is 2 meters. And then there's another 5.5 millimeters to the nodal point. So it'll be 2,000 millimeters and 5.5 millimeters. So here's the whole setup. We've got 2005.5. We got 17. We have 1.7. There's the nodal point. The only thing we don't know is, how tall is this X that's been projected from the eye. So we do similar triangles. 1.7 over 17 equals X over 2005, and then multiply it out, and the answer is 200 millimeters or 20 centimeters. So this object is 20 centimeters, 20 centimeters high, or 200 millimeters. And so the blind spot is 200 millimeters in size when projected 2 meters from the eye. So we did it. We've made it through part 1 in less than 90 minutes. Which I know it may seem like it's been 3 hours. Now I might normally take a break here, but I'm a little worried about if I stop my live stream, I'm not going to be able to get it started again. So I don't know. I might just keep going. I'm just going to keep going. I mean, the rest of you I won't know if you sneak out or maybe I do, if you slip out for 30 seconds to get a sip of water or use the restroom or something. So part 2 is, we're now getting more practical and into refraction, visual acuity testing, talk about astigmatism, refractive surgery, all that we need to know about refraction. So let's talk first about visual acuity testing. And before we talk about that, I just want to remind you again of a little bit of high school math, which is, we all agree that 1 degree is 1/360th of a circle. And then if we take that 1 degree and break it up into 60 pieces, then we have 1 minute of angle. So 1 minute of angle is 1/60th of a degree. And if we take that minute of angle and break that into 60 pieces, then we have 1 second of arc. So 1 second of arc, 1 arc second, is a 60th of a 60th, or 1/3600th of a degree, is 1 second of arc. So when measuring visual acuity, we have what we think about when we think of visual acuity is the minimum resolvable acuity. That is your ability to see a letter. And that is 1 minute of arc resolution. Whereas there is also just minimum visible acuity. That's your ability to see that there's something there. Like you don't know what letter it is, but you know there's a letter. And so that's much less. That's only 10 seconds of arc, or 1/60th of a 1/6 of a minute. And then there's vernier acuity. And notice that vernier acuity is even less than, you can actually see a break in a, that's your ability to see a break in a line. And that's just 3 to 5 seconds of arc. So it's easier to see a break in a line than it is to see a spot in a wall. Or you can see a break in a line that's smaller than what you could see if you were just looking for a spot on the wall. So vernier acuity is our most precise measurement, or our most precise way of using our eyes. That separation is less than the separation of photoreceptors in our retina. So it's using the integrating part of the retina to look at the whole line and figure out if it's broken or not. So vernier acuity, and as a result, we use vernier scales when we need to make very precise measurements, and we can now use them for golf balls, for golfing. Now we have a problem because I haven't figured out how to get out a laser pointer. This particular video has to, I need to be able to click on it to be able to start the video. It's more just for humor anyway. It was just to show we can use these vernier golf balls to become better golfers. Most of my videos auto-run, but this one just did. So question, how much of a visual angle does the 20/20 subtend? I just gave you a hint to the answer when I talked about our minimum resolvable, minimum resolvable acuity is 1 arc minute. And so the 20/20 subtends 5 minutes. Each leg subtends 1 minute, 1 arc minute of visual angle. So for the old-fashioned wall chart that you nailed to the wall 20 feet away from the person, that 20/20 needs to be 8.73 millimeters tall to subtend 5 minutes of angle. But as you change your distances, get closer and further, then your visual acuity, obviously, the calculation changes. So a 20/20 subtends 5 minutes of visual angle. A 2200 subtends 50 minutes of visual angle. So a patient with 2200 acuity can read the 20/20 line. They just have to get 2 feet away, because 2/20 vision is the same as 2200 vision. So speaking of visual acuity, I just want to take a little digression and to think about when we are checking vision in kids, because we can't measure visual acuity in kids, but we do know that kids have vision. There are ways to test it using, as I'll show you. But at birth, all you really expect to get is a pupillary light reflex and a blink to light. So you don't really expect to see any eye movements whatsoever. By the time they're anywhere between 2 and 6 weeks old, you start to get a response to like an OKN drum or a moving stimulus. You don't really see fixation and following until they're more like 4 to 6 weeks. If there's nothing by 3 months, you begin to get a little worried. Same with fixation. So fixation and following really need to be there by 3 months and probably a little bit before that. We have some sense of visual acuity from using VEP, visually evoked potentials, preferential looking cards, to be able to estimate that. And so we made this app that we call Baby-C that gives a live video simulation to new parents of what their infant's vision is. So just kind of a fun project, taking some of the information that's out there. So that's the Baby-C app. I think, yeah, it's now on Android. We finally were able to pay some programmers to get it onto Android too. So this is one way that we figure out infinite vision babies. We use these teller acuity cards. So she's looking to see how the baby responds, because the baby is naturally going to look at the card that has the grid pattern on it. And so then she peeks through the little peephole to see which way he's looking. So you see there's a grid pattern there, but not on the other side. And the grids have finer and finer measures. And so when they start randomly responding, that's when you know they're not seeing it. So once you get past that, then we can start to get, when kids get older, now we can start to get into optotypes. So we have picture optotypes. These are the Allen figures. We have the Leia symbols. Then as they get older, there are letter optotypes. The tumbling E has pretty much fallen out of favor. I think it's confusing for kids. They tend to do better going straight from picture optotypes to the HOTV letters. And he doesn't need to know his letters. He just has to match the letter that he has on his lap with the one that he sees on the wall. So what's special about the ETDRS visual acuity chart? I'll just pause for a second. All right, so the ETDRS visual acuity chart is different from the Snellen chart in that the letters are of equal viewing difficulty. Snellen, that's not the case. Each line has 5 letters. You see Snellen, that's again not the case. The spacing between letters equals the letter size on that line, and the optotypes change in 0.1 log unit increments, so that no matter where you are on the chart, a 3-line change is a doubling or halving of the visual angle. So this chart is used in research studies in particular, because that 3-line change then is meaningful and consistent and comparable across patients who may have different visual acuities to start with. All right, so we'll move to refractive error and correction of refractive error. So remember, we talked about the secondary focal point in the schematic eye. For the secondary focal point, accommodation is completely relaxed, and then that should fall on the retina. It's supposed to. By the way, I did try Control L. That doesn't seem to be the answer. Arrow icon in the top left corner to return to the cursor. I don't see that either. So if the focal point does not fall on the retina, then we have refractive error. So if the focal point falls in front of the retina, then you have myopia. If it's behind the retina, you have hyperopia. So why would you have myopia? Well, either the eye is too strong or the eye is too long. So if the eye is too strong or too long, then the focal point, secondary focal point's in front of the retina and you're myopic. If the eye is too weak or is too short, then the focal point falls behind the retina and you have hyperopia. So the other way to consider refractive error is, instead of in terms of focal points, if we can think of it in terms of the far point. So if we track the light backwards through the eye, we start at the retina and track backwards, then the rays of light emerging should be parallel rays of light. And so that would be in the emmetropic case. On the other hand, if you have a myopic eye, the eye is too long or too strong, then you have too much power up here. So instead of parallel rays of light emerging, you have converging rays of light emerging. And for hyperopia, the eye is not strong enough. And so you have the rays of light as they leave the eye are still diverging because there wasn't enough power here. So then you create imaginary extensions of the rays of light back to a point of intersection somewhere behind the eye. So hyperopic eye, you have a virtual far point behind the eye. Myopia, you have a far point in front of the eye. So when you have a patient who has a refractive error like this, you need to correct it. And when we think about how to correct it, we construct your thinking behind how to correct it by imagining that you're finding a lens whose focal point aligns with the far point of the eye. So you have a myopic person. They have a far point here. So we're going to choose a lens whose focal point coincides with the far point, and then you place it such that occurs. So the reason that I describe correcting refractive error this way is that it tells you that not only does the power of the lens matter, but the position of the lens with respect to the eye matters. So you can choose a different power lens. You just have to place it in a different place in front of the eye, and you can still correct the refractive error. So we'll see examples of that in just a minute. So for a myopic eye, choose a plus lens whose focal point aligns with the far point of the eye. For a hyperopic patient, you choose a plus lens whose focal point aligns with the virtual far point behind the eye. And it's important to remember the far point of a myope is in front and the hyperope is in back when doing your vertex distance questions. So we're going to talk about lens effectivity and vertex distance then. First, we have a question. So if a +10 lens is moved closer to the eye, does it have more effective power or less effective power or the same power? Well, I hope you're not thinking it has the same power if it's moved closer to the eye from what I just said. So if we move it closer to the eye, does it have more effective power or less? Well, let's look at an example. And then what about a -10 lens? Is it going to have more effective power or less when it's moved closer to the eye? I'll tell you that the +10 lens is less effective when it's closer to the eye. The -10 lens is more effective power when it's closer to the eye. So we'll show you what I mean. So here's a +10 lens. It's correcting this refractive error. So the focal point of the lens coincides with the far point of the eye. If we slide that lens forward, now 10 diopters isn't the right power. Now 10 is too strong because you need a longer focal length. So we're going to drop it down to +9, and now you have a longer focal length. So now that coincides with the far point of the eye. So we only need a +9 when we're further in front of the eye, but we need a +10 when we're closer to the eye. So it has less effective power when you get closer to the eye because you need a higher number to correct the same refractive error. So moving plus lenses towards the eye decreases the effective lens power. Another way to think of that is that you kind of know intuitively that an aphakic spectacle is going to be in the +10 to +12 diopter range. An aphakic contact lens is going to be in the +15 to +17 range. And an intraocular lens is going to be +18 to +20. So you can answer this question intuitively by just thinking about the difference between an aphakic spectacle and a intraocular lens. So we can, we need to know how to do these vertex distance corrections, because remember, that's one of the top 10 questions. And so here's an example. We have a patient who's wearing 12.5 diopter aphakic spectacles with a 13 millimeter vertex distance. That's the distance between the lens and the cornea. They want to switch to contact lenses. So what power of contact lens do you expect they're going to require? Well, we go back to our first rule of optics. When in doubt, take a reciprocal. So we know that we take a reciprocal at 12.5. 1 over 12.5 is 0.08 or 80 millimeters or 8 centimeters. So we know that because this person is corrected by a 12.5 diopter lens, that the focal length is 8 centimeters, that the far point of the eye is 8 centimeters behind the lens. Okay, now we want to move this lens closer to the eye. So we're going to shift the lens closer by 13 millimeters. So the new lens is going to be 80 minus 13, or only 67 millimeters away from the far point of the eye. So we need a stronger lens. How strong? 1 over 0.067 meters is plus 15 diopters. So when doing these vertex distance corrections, we take 3 steps. First, you take a reciprocal of the lens. Second, you add or subtract the new distance, depending on if it's a plus or minus lens, and if you're switching from glasses to contacts or vice versa. And then third, you take the reciprocal of the new distance, and that gives you the new power. What about a minus lens? Well, moving a minus lens forward decreases the effective minus power. So I have my minus lens spectacles that I'm wearing now, and as I move them away, I'm getting less and less correction. Whereas if I was a hyperope, if I were to move these away, I'd be getting more and more plus power. But for a myope, I'm getting less and less minus power, which is actually the same as getting more plus power. So whether it's plus or minus lenses, you're getting more plus power, but that makes the minus lens weaker and a plus lens stronger. All right, what about accommodation? So we'll talk about the physical properties of accommodation, how to measure it, and then prescribing bifocals. So the question here for you is, which of these apes is more hyperopic? And so we can imagine that it's this guy. And in this study, wild long-sightedness in old wild bonobos during grooming, they looked at the whole colony and figured out their age by how far away they were sitting from their mates when they were dining on their insects. So inevitably, accommodation does reduce with time because of the nature of the lens. So what is accommodation exactly? Well, I came up with this animation. So here's the plane of the retina. And although this lens may be perfectly sufficient to focus parallel rays of light onto the retina, as you move an object closer, you have more diverging rays coming in, so you need more vergence to converge that light in time to get to the retina. So the ciliary muscle contracts, this relaxes the zonules, the lens takes up more and more of a round shape, and the image gets focused more onto the nearer target. So it's ciliary muscle, but it depends on the lens to be pliable and to change shape. And with age, as the lens hardens, it changes shape less effectively, even though the ciliary body is still working and the zonules are still attached. But that's the basic idea, the Helmholtz theory of accommodation that most of us still believe in. There are some skeptics on this topic, but for our purposes, that's what we need to know. So there are now some accommodating IOLs that try to take advantage of the fact that the ciliary muscle does still contract when we accommodate. So this now, the basic concept here is that you get more effective lens power when the ciliary muscle contracts. If you can get the lens to like shift its position, to shift forward, you'll get more plus power and then therefore get effective accommodation.
As the ciliary body relaxes, zonules pull the haptics flat, moving the optic backwards. When the ciliary body contracts, the haptics vault the optic forward.
So that's
in this way, the Z lens moves back and forth in much the same way that the natural lens does during accommodation and disaccommodation.
So that's the one way to do that. Now there's most of these accommodating IOLs, though, have been generating only about 0.4 diopters of accommodation. So not what we're hoping for, although a friend of mine, Jim Ellis, thinks he has a better idea, and he calls it the jealousy lens. So let's see what it still has the same basic idea of vaulting the lens forward, but also changing its curvature in this case to get
the eye in a folded shape and unfolds into the capsular bag. When the eye changes focus from near to far, a small amount of force is applied to the lens capsule by the zonules as the ciliary muscle relaxes. This causes the lens to flatten and increase in diameter. However, due to lens capsule fibrosis, which is inevitable following cataract surgery and IOL placement, no more than a ½ millimeter of overall diameter change occurs when the eye transitions from near focus to far focus. The innovative optical design of the Jelly-C lens enables focus to shift from very near to far with only a fraction of a millimeter in diameter increase. Its haptics are designed to lock into the fibrotic peripheral lens capsule so the natural accommodation mechanism can work effectively. As a result,
so I have no financial interest in that entity, but it's kind of moving the accommodating IOLs forward. I think it's not current; it's still going through FDA, et cetera. Small aperture IOLs have been another way to try to get accommodation and to enhance the quality of the image. But it can make it harder to examine patients, and it seems that the small aperture IOLs can also reduce contrast sensitivity. So a question, what is the technical definition of the far point of the eye? So we've already talked about the far point and what it is, but there's a technical definition, and if you've heard this lecture before, you might be able to say this, but I just want to at least give you a pause. The far point of the eye has to do with optical conjugacy. It's a point that's conjugate. And what about the near point? Well, let's see. So the far point is the point on the visual axis that's conjugate to the retina with accommodation completely relaxed. And the near point is the point on the visual axis that's conjugate to the retina with accommodation fully active. So knowing that, we can do some calculations of amplitude and range of accommodation, which we sometimes need to do. And so how do we measure accommodative amplitude? Well, we got two questions. We've got two questions for in short order here. How is accommodative amplitude measured? Well, what we do is we we can do it with this attaching this Prince rule to the phoropter. and then you dial in the distance correction, and then slowly move this card forward, closer, 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 until he says it first starts to blur, because as soon as it starts to blur, then he's no longer following it when he's accommodating. So now often though, in people who you want to measure the accommodative amplitude, they can't accommodate anywhere on this. They can't dial in anything. So sometimes you have to give a little bit of a boost. So for example, you might take the distance correction, but then add, say, 2 diopters. And so then you would put this lens 0.5 meters away, and then they would be in focus on it with the accommodation completely relaxed. The card would be in focus at 0.5 meters away. And this Prince rule is actually labeled both in centimeters and in diopters. Then you move it closer, 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 closer until it starts to blur. So let's say you started at the 2 diopter point, and then it starts to blur at the 3 diopter point. Then that person has an amplitude of accommodation of 1 diopter. You do it at one eye at a time, not both eyes simultaneously. And that's your measure. So you do have to know their distance correction in order to measure it, though. So let's look at an example of range of accommodation and just how to measure range of accommodation in a person who has 4 diopters of hyperopia and an 8 diopter amplitude of accommodation. So this is the eye. So they have 4 diopters of hyperopia. So they have a virtual far point behind the eye, 25 centimeters behind. So they've got an 8 diopter amplitude of accommodation though. So they're going to use up 4 diopters of that 8 just to be able to see clearly at infinity. And so then they've got 4 diopters left. So they can exert 4 more diopters. And so then when accommodation is maximal, the near point is going to be 1/4 diopters or 25 centimeters. So the range of accommodation of this eye is from infinity up to 25 centimeters away. What about for a myope? How does it work for a myope? Well, so an eye with 4 diopters of myopia, it's sort of like you've got accommodation built in. It's like there's 4 diopters of accommodation built into your eye. So your far point is already 25 centimeters away. And then you got all 8 to work with to put on top of the 4 that's already built in. So you're going to get 4 plus 8 is 12. And 1/12 diopters is 0.083 meters or 8.3 centimeters. So the range of accommodation of this myope is from 25 centimeters up to 8.3 centimeters. So you see, for range of accommodation, we use 2 numbers. For amplitude, it's just 1 number. Now, what if you gave this person their glasses? They put on their 4 diopter myopic glasses. Then their range of accommodation is going to be from infinity up to 1/8 of a meter away. And that would be true whether they were the hyperope or the myope if they had their glasses correction in place, because they've got an 8 diopter amplitude of accommodation. Now, when we have a patient who needs bifocals, do we always need to measure their range of accommodation and try to make some decisions on that? No, not always. In fact, not often. But we can, if you. So the most rigorous way to do it is you measure the amplitude of accommodation for that person, and then you take the reciprocal of their preferred working distance and subtract half of their accommodative amplitude. So say they've got a 2 diopter amplitude of accommodation. Well, then that means that they can focus up to 50 centimeters away. But that means they're like they're really cranking it in to see 50 centimeters away. So that's going to be fatiguing over the course of the day. So you only want them to have to use one diopter of accommodation that they've got left. So then that would be 1 meter away, but that's not good enough for reading. So then you would add another, if you added another 1 diopter on top of that, then you get them back to being able to read comfortably at 50 centimeters. If they prefer to read closer at 33 centimeters, then you got to put 2 diopters on top of that to prescribe bifocals. So that's the rigorous way to do it. You can also use tables and anticipate that a 40-year-old has 6 diopters and a 60-year-old has 1 diopter, and do that accordingly. Or, you know, just trial and error in the office, which is sort of what we do most of the time. But if you have a rare case, you have a patient who's a latent hyperope, a young person who's struggling at near, something isn't quite right, then you want to be able to know how to do this. And that reminds me just of, generally speaking, like, why are we even studying all of this in so much detail? And I think that, you know, really anybody can take care of most of the patients. You know, you can kind of get by and take care of 90% of patients without knowing that much. But if you want to be able to help that last 5 or 10% of patients, that's where you've got to, you know, really dig in and know and understand some of the things that we're doing here. Try to make it worth your 8 hours of time, or 6 hours, I guess. We're not going 8 hours, but we may go 6 hours. So it's hard to know. So now we're still in refraction, but we've made it to astigmatism. And I think, you know, I think maybe it is worth, I'm going to take a chance, and I'm going to try to, let me see if I can pause the live stream. Hang on a second here. More. Don't want to end it. Says stop live stream. All right. So we're gonna try it, and then I'll stay in touch with you through the chat. We're gonna stop the live stream, and then I got it going once, I'll get it going again. So we are back. Yay. I was able to get back in. And I have some very exciting news. It's an undocumented feature. I just hit hold control to get the, whoops. 1 second. Hold control to get the mouse, of course. I mean, to get the laser pointer. But if I do control and then roll the mouse up and roll it back down, then the laser pointer stays on. And then to get it off, I just hit escape. So back to astigmatism. Just making sure I'm on. Yes, we're back. So now I know I can take another break if I want to. We're going to talk about cylindrical lenses and all the things you see here. So cylindrical lens is literally a cylinder. And so how is it that a cylindrical lens creates such havoc in our lives? If we were all just spherical eyes, refraction would be so much easier. So to understand how a cylindrical lens works, and this took me a long time to figure out. I'd been given this lecture for like 3 years before I knew what it was doing. We have to imagine that a beam of light can be broken down into parallel rays, a series of parallel rays. And if you first think of it as a series of parallel vertical rays, And then we think of it as a series of parallel horizontal rays. So first, let's imagine a series of parallel vertical rays. And we're just going to imagine one single parallel ray of light. All right. And when that comes and in a vertical oriented ray of light, piece of a ray, plane of light, is going to just see a flat surface. So it's just going to, the flat surface, it's going to slow down inside of this lens, and it's going to speed up, and no refraction took place at all. But a horizontal plane of light is going to see that curved refractive surface. So it's going to get refracted into a point, and then off it goes. And a plane above that, it's going to have the same thing happen. And the plane below that, the same thing. And a plane, and the infinite number of planes seeing the horizontal surface of this lens all get focused into a single focal line. This focal line of this cylindrical lens is parallel to the axis and perpendicular to the power. So that is a cylindrical lens. Now you can have a spherocylindrical lens where we have a little bit of power on the vertical meridian too. So then all the vertical planes, instead of seeing zero power, they get a little power too. So they get refracted to a horizontal focal line that's a little bit further away, because in this case, the curve is not as much as the horizontal curve. And so from that, you go from the vertical horizontal line through some elliptical and round shapes to a horizontal focal line. And that's called the interval of Sturm. So what is the circle of least confusion? Just jumping right in with these questions. Like, you've heard about it. You kind of know what it is. Like, there's the what is it conceptually, and then there's the what is it like mathematically. So I guess I want both. So conceptually, it's called this because it's where the letters are believed to be most recognizable, because instead of having a lot of vertical distortion on the vertical focal line or a lot of horizontal distortion on the horizontal focal line, you get equal distortion. So the letters are blurry, but they're not distorted at the circle of least confusion. Mathematically speaking, it's the halfway point in diopters between the two focal lines. So if this stronger focal line is 4 diopters away, and this weaker focal line is 2 diopters away, then the circle of least confusion is going to be 3 diopters away. So 25 centimeters, 33 centimeters, and 50 centimeters. So that's the circle of least confusion. Now, John Jackson here demonstrates this for us. So let's watch this little video.
So here is my image screen with my astigmatic system. And as you can see, if I move the screen to this position, I get a vertical line on the screen. And as I keep on going, I get to a circle on the screen. If I keep pushing it back farther, I get a horizontal line on the screen. So those are my 3 marker locations with inside Sturm's conoid. I have the line closest to the lens, the near line, the circle of least confusion, and then finally the far line. So that's what they look like on the bit.
It's just great to see so many earnest people out there making videos for me to borrow for this presentation. So just as remember how we talked about how you correct refractive error by choosing a lens whose focal point matches the far point of the eye. Well, an astigmatic eye is not going to have a far point. It's going to have far or a focal point. It's going to have focal lines. So there's going to be 2 focal lines and 2 meridians. Or if you turn the light around the other way, you're going to have 2 far lines. And so when you want to correct it, you need to choose a lens whose far lines coincide, whose focal lines coincide with the far lines of the eye. So when we have an astigmatic lens, as you saw, we have an axis. Remember, the axis is parallel to the focal line, perpendicular to the power of the lens. And so when we define our axis in terms of degrees, and this is showing it's 90 degrees is up top, 180 to the left, and then it starts over. And that's symmetric. Both the red light, I mean, it's not symmetric, it's the same. The right and the left eye both have the same scale with 30 degrees at the 2 o'clock point. So every 30 degrees is another clock hour on astigmatic axis. Now, when we draw astigmatic lenses, you can't just use one number. We have the cross diagram. So principal meridians are labeled with the power acting in those meridians. That is to say, here's our cylindrical lens. And so you see there's power of +1 diopter. Here's the axis of the lens. And then here's a +3 diopter lens. So you're going to have the power cross is going to be along the power cross is going to be where the most curvature is. So this +3, the axis is over here, but the power at 135, but the power for this +3 is going to be at 45. So this is a power cross, +3 acting in the 45-degree meridian, +1 acting in the 135-degree meridian. That's the power cross. But then we also sometimes have an axis cross. And so in this case, then it's +1 axis, 145, +3 axis, 135. So there's room for some confusion here, but it's, generally speaking, you do work through a few problems, you get the hang of it. If you ever take a cylindrical lens, just try pulling one out of the trial lens set. And you can feel the curvature of the lens and see that it's opposite of the axis. So sometimes that can help to reinforce it, is to have that tactile sensation of massaging an astigmatic lens. You can just imagine, with my love of optics, me after hours massaging the astigmatic lenses. So we have the cross diagram. So this is a power cross diagram, and you'll hear me mention stenopeic slit refractions later. When you do a stenopeic slit refraction, you end up with a power cross like this. And so now we need to convert this power cross to a glasses prescription in spherocylindrical notation. So to do that, it takes a few steps. So first, we're going to take this spherocylindrical and split it back out into two pieces. So that's the same as this is the same as a +2 pure cylindrical lens combined with, that's the combined with symbol, combined with a -1 spherocylindrical lens. We just add across meridians to make sure we did that right. 0 + 2 is 2. -1 + 0 is -1. So this combination is the same as this power cross. Now, it doesn't really give us, it's not proper spherocylindrical notation though. It's just +2. And notice this is +2 in the 90-degree meridian. So that's +2 axis 180 combined with -1 axis 90, combination of two cylinders. That's not spherocylindrical notation yet, though. We've got to do something to make one of these two into a sphere. So let's say we're going to take this one and make it into a sphere. So we'll pull another cylinder out of our hat. And we're going to add that here. So now we've added a cylinder here and a cylinder here. That makes it into a sphere. But what we give to one side, we don't want to change the power of the combination. So now we've given +2 to this side. So we got to take +2 off of this side. So that -1 turns into a -3. Now, did we do that right? Well, -3 + 2 is -1. Good. 0 plus 2 is 2. Good. So this combination is the same. And now we have spherocylindrical notation. We have plus 2 sphere combined with minus 3 in the 180 meridian or minus 3 axis 90. There. Plus 2 minus 3 times 90. When we write it out as a glass subscription, we usually just drop the combined with symbol. Now we could have chosen to make the minus 1 as the sphere. So let's try that. So we're going to take the minus 1, here it is down here again, and we're going to put a minus 1 cylinder in the vertical. Let's pull that in. Oh, there it is. So now we've got minus 1 sphere, but we can't change the power of the combination. So we've got to take a minus 1 and put a plus 1 over here to balance that out. So plus 2 plus 1 is plus 3. So now we've got plus 3 lens here. So did we do that right? Negative 1 plus 0 is negative 1. Good. Negative 1 plus 3 is positive 2. Good. So now we've got minus 1 sphere combined with plus 3 in the 90-degree meridian, or minus 1 plus 3 axis 180. So that's spherocylindrical notation in plus cylinder form. This is in minus cylinder form. It's all the same lens written out 4 different ways: a power cross, a combination of 2 cylinders, spherocylindrical plus minus cylinders, so the spherocylindrical plus cylinder. And you can convert from plus to minus cylinder fairly easily. I think I'll show that later. Now, what if we've got our glasses prescription and we want to make it into a power, we want to go the opposite way and make it into a power cross. Every now and then we need to do that. You'll see some examples later today, or by the time I get to it, it'll feel like it's 2 o'clock in the morning. So we just draw 2 power crosses, right? Because here's the plus 2 sphere. Okay, draw it like that. Plus 2 sphere means we got 2 on both meridians. And then we got minus 3 axis 90s. So minus 3 in the 180-degree meridian. Did we do that right? I think so. Okay, so now what? Now we combine by adding across meridians. So minus 3 plus 2 is, plus 0 plus 2 is plus 2, and negative 3 plus 2 is negative 1. And there we are. We found our way back to a power cross from a glass subscription. Now, there's a quicker way to do it, though, and that involves converting from plus to minus cylinder. So, which I guess I didn't tell you yet. So now I'm going to tell you, to convert from minus cylinder to plus cylinder, the new is 3 steps. It's a lot of 3 steps today. So the new, to convert from minus to plus, the new sphere is the old sphere plus the old cylinder. So 2 plus negative 3 is negative 1. So the new sphere is that combination. The new cylinder is same as the old cylinder, but with opposite signs. I forgot to use my laser pointer after all that. The new axis is 90 degrees away from the old axis. So now we've written this out. My permanent pointer back. Now we've written this out in plus and minus cylinder form. So next, what we do is we actually just take the plus, we take the sphere and you put it right on the axis with the number that goes with it. So you can put the plus 2 on the 90-degree meridian, and you put the minus 1 on the 180 meridian. And this was just sort of an accidental discovery, if you will, a shortcut. But it comes in handy because then you can just eyeball a prescription and say, oh, okay, we got plus 2 in the 90-degree meridian. And maybe sometimes that's all you need to know, as you'll see when we're talking about induced prism in eccentric gaze. So that's why I've belabored the point here to make sure you understand it. Now, when we do retinoscopy in pediatric ophthalmology, a lot of our kids won't sit at a 4-opter. And so you're doing your retinoscopy, you do your intercept. So it looks like we've got neutralization there. And let's say we needed a 250 lens to neutralize in this meridian. Okay, this time we're going to write it on an axis cross. So if we neutralized, we're actually neutralizing the vertical meridian. And so we're writing it on the axis cross at plus 250. So this, and again, it becomes intuitive when you do it enough, but the horizontal, the number you get when you're holding it horizontal, you're sweeping vertically, so you're neutralizing the vertical meridian, but you're putting it on the 250, that's a 250, so you're putting it on the axis, which is like the less you think about it, the better. You just, the line's this way, you put it on that line. Good. Now we rotate it 90 degrees, and we discover that in this child, a 450 lens neutralizes in this meridian. It's like, okay, 450 this way. So we're just going to put the 450 on that line. Great. There's our axis cross. So is that our prescription? No, not yet, because that's our gross prescription. So then we can do that whole thing that I just did and draw it out and do it separately. But now we've done enough times, we're just going to like do the quick way, which is to say, okay, we want plus cylinders, so we'll find the lowest number first, plus 250, and then you got to add 2 to that to get to 450, right? So 250, we're 2 away. So it's plus 250 plus 2 to get up to axis 90, since this is an axis cross. And there's your prescription. But wait, we forgot something. This is retinoscopy. We've got to take away our working distance. And so for me, that's 2/3 of a meter. So the net retinoscopy, which is 1.5 diopters. So I have to take away my 1.5 diopter working distance, and there's our prescription. 1.00 plus 2.00 times 90. This is where the pediatric ophthalmologists have a leg up on the optics section of the exam, because like we're forced to do this every day over and over. Whereas, like, I don't know, do the retina docs know where the retinoscope is? I don't mean to be casting aspersions. I'm just saying you're doing like important retinal surgery. So you perform an over-refraction of a lens with a power of plus 0.25 plus 1.00 times 85, and find there's an additional cylinder of plus 0.50 times 113. How do you determine the new prescription? Well, that's not an easy one. There's a lot of numbers on this page too. So what you do though is you don't have to worry so much about the numbers. You could worry about the numbers, like you can find these online, you can find calculators where you put in the over refraction on top of the glasses and the number pops out. But what Dave Guyton taught me was to just take the whole thing, the lens, the clip, the extra lens, and then you put the whole thing in the lens meter. And now you can just read the new prescription right off on the lens meter. There is sometimes, though, I've seen questions pop up where it is intuitable, where you can do it in your head because the cylinders more or less line up with each other. Like they might try to like throw it off by 5 degrees or something just to scare you. But it's close enough that you can get away with adding them. In this case, I'm not putting them off by 5 degrees. I'm just saying you got this lens, a 450 in one meridian and one in the other, and then you got this lens, and you want to combine these cylinders, well, you just add them up like we just did, you add across meridians. So 450 plus 1 is 550, 450 plus 1 is 550, and so the net combination here is a spherical lens. So I can see someone throwing that at you, and just so you can show that you know how to add across meridians. Now, there are different, we can just describe astigmatism using certain terminology. The whole fact that there's the plus cylinder world and the minus cylinder world, like most optometrists I've found tend to be in the minus cylinder world. Most pediatric ophthalmologists seem to gravitate toward plus cylinder. I think it's easier with the free lenses to be holding up plus cylinders. And but there's plus cylinder and minus cylinders among all of us. I actually normally have that in my, in my name thing on the Zoom. It's like David Hunter plus cylinder, like in parentheses, plus cylinder. But in order to describe different types of astigmatism, then you need to have a language that doesn't rely on whether you're a plus or minus cylinder. So that's what this that will have to do, especially with and against the rule. But also we can talk about astigmatism as mixed. In that case, one focal line is in front of the retina and one is behind the retina. But then compound myopic astigmatism, both focal lines are in front of the retina. So you're like all in myopic astigmatism here. And then compound hyperopic, both focal lines are behind the retina. And then you can have rare cases where it's simple myopic, where one focal line is on, one's in front, and simple hyperopic, where one focal is on and one is behind. So these are the types of astigmatism: compound, myopic, etc. And you can figure that out as we will from looking at the power cross. This is where the plus and minus cylinder people might differ. So, and that's why we have to say with the rule is when you have a steep cornea vertically, because if you're plus cylinder, that means the correcting cylinder is in the vertical meridian. Minus cylinder, the correcting cylinder is the horizontal meridian. So in pediatric ophthalmology, we see a lot of plus cylinder kids running through our office. I guess in glaucoma, older patients tend to have more against the rule. So, all the rest of you are seeing more maybe against the rule astigmatism. So, and then oblique astigmatism is anything that's not 20 to 70 or 110 to 160. So oblique, outside of plus or minus 20 degrees. So here's a prescription, and my question for you. Oh, I didn't put a gritted teeth emoji, even though I'm going to make you work here. So we have a prescription: +2, -3 times 90. Is that simple astigmatism, compound myopic, mixed? How do you know? Well, what I do for these, like we already know that the +2, there's going to be a +2 on the 90-degree meridian. Let's write it out in minus cylinder form too. So the new sphere is the old sphere plus the old cylinder. So -3 + 2 is -1. The new cylinder is the old cylinder with opposite axis. The new axis is 90 degrees away from the old axis. So now we've got a +2 on one meridian and a -1 on the other of the power cross. So that's mixed astigmatism. Good. How about the next one? +2, -2, axis 90. Well, let's write it out in plus cylinder form. So the new sphere is the old sphere plus the old cylinder. So +2 - 2 is plano, 0. New sphere is the old sphere, same as the old cylinder, new cylinder, same as the old cylinder with opposite sign, new axis 90 degrees away from the old axis. So this power cross is going to have plano on one and +2 on the other. So that is a rare case of simple hyperopic astigmatism. And then finally, you got plus 2 minus 1 times 90. We're going to write that out in plus cylinder format. So new sphere is old sphere plus old cylinder. So plus 2 minus 1 is plus 1. New cylinder is opposite of old cylinder, same amount. New axis is 90 degrees away from the old axis. So this power cross is going to be a plus 2 and a plus 1. They're both plus. So that's compound hyperopic astigmatism. And then in each of these cases, the plus cylinder is at 180. And so if the plus cylinder, correcting plus cylinder is at 180, then that must be against, against the rule of astigmatism. Well, finally, here's the spherical equivalent slide. Is sphere plus half of cylinder. So in each of these cases, we want to know what's the spherical equivalent, because that's what places the circle of least confusion on the retina. So generally speaking, if you don't have any cylindrical lenses available, or you have reason to not want to give the astigmatic correction, you give the spherical equivalent, that's sphere plus half cylinder. So if we just quickly, the spherical equivalent of, say, this one is going to be plus 2 minus 1.5, which will be plus 0.5 diopters. Oh, a question. Let's make sure nobody's typing to me. You perform keratometry and find that the corneal power is 40 degrees, 40 at 30, that is 40 diopters in the 30-degree meridian, 46 in the 120-degree meridian. What sort of astigmatic correction would you expect to see? Well, how many diopters would it be, first of all? Anybody type it in? No. Not yet. Maybe they did. I may be on a lag. So it should be about 6 diopters. That's the easy part. Now, what axis or meridian would you expect it to be? Well, it's, here's the numbers again. 40 at 30, 46 at 120. So if you want to get rid of the difference, you've got to either put 6 more in the 30-degree meridian or put minus 6 in the 120 meridian. So we're disregarding spherical equivalent changes here. So let's say minus 6 at 120. So you would need to put minus 6 in the 120-degree meridian. And so to put power in the 120 meridian, you'd need axis in the 30-degree meridian. So your prescription would be blah, blah, blah sphere minus 6 axis 30 for this keratometry. And this may sound obtuse to be focusing on this, but it actually can matter in real life because not all astigmatism is corneal. And there may be cases where you need to reconcile whether the keratometry matches the correction that patient needs. So you need to be able to do this sort of a calculation to make that happen. Now, how do tight sutures cause astigmatism? Well, this again is something that it took me a while to figure out, but normally when we have a corneal incision and we close it with a suture, I know you don't do that much anymore, but it still happens sometimes. We want to tie that just right. Right? You want to just tie it just right without changing anything. But if you tie the suture too tight, then you're going to change the corneal curvature. You're going to cause it to warp. And so what happens is when you tie that suture super tight, you actually flatten it where the suture is, but then you get a compensatory steepening of the rest of the cornea. And the rest of the cornea is the part that's over the pupil. And so even though the tight suture has actually flattened the area where you tied it, it steepens the rest of the cornea. And so it causes more curvature in the meridian of the suture. So that because this distance isn't going to change, but yet you flatten it here, just imagine there's a big foot there stepping on the edge of the cornea. Step on the edge of the cornea, you're going to warp the rest of it to make it steeper. So that's tight sutures and astigmatism. And then there are two lens aberrations that are worth thinking about at least a little bit. One is spherical aberration and one is astigmatism of oblique incidence. So spherical aberration, if you look at this lens, you see, just looking at it, that it's more curved at the edge than it is in the middle. And so since it's more curved at the edge, parallel rays of light coming in the edge here are going to experience more power than the rays here in this closer to the center. And so you're going to end up getting distortion of the of your image because of that differential focusing. We see that in the eye, especially in kids whose pupils dilate so widely and they've got nice clear lenses. You'll see you'll still have with motion in the center when you're doing your retinoscopy, but you've got against motion in the periphery. And it can be kind of confusing because what do you prescribe? It's like, do you keep going till all the width is gone, or do you stop when you start seeing a little neutralization in the periphery? The answer to that is almost always you focus on the center, because after the dilation wears off, that's where the refraction is going to be. That's the part of the eye that's still going to be contributing to the refraction. The other place spherical aberration matters is in indirect ophthalmoscopy. We've got that little white ring on the bottom of the indirect lens. That's because these are aspheric lenses. They're specifically designed to not create any aberration when you're looking at it, when you're looking at the retina. But if you flip it upside down, look at that, you get all this distortion in the periphery from spherical aberration. And so, yes, greetings back to Dr. Tandili in Albania, who is tuned in. Astigmatism of oblique incidence happens when you look obliquely through a lens. So you see I've got this minus lens, and when I tilt it, then you get this, it blurs the image because we're inducing additional astigmatism. This is a spherical lens. Takes a second for the camera to refocus, but then as we tilt it, you see that you get that astigmatic effect and blur. So when you tilt a minus lens, you're inducing minus cylinder with the axis and the axis of tilt. And when you tilt a plus lens, you're inducing plus cylinder with the axis and the axis of tilt. So differential diagnosis of refractive error. I'm going to just pause and ask you to think about what's the differential diagnosis of acquired or progressive, of increasing myopia. So you have a patient who's comes in, you do your refraction, you're confident about it, and then they come back 4 months later and they've got another diopter of myopia, and they're not necessarily kids. So what are some things that could cause that? We have keratoconus typed into the chat. That's a good one. I'm just looking to see if anybody we had an auto spell check to staphylococcus, but yes, staphyloma. Accommodative spasm. All right, that's good. So here's keratoconus. So you see you get a steeper lens. So that's going to add plus power. It's going to make the eye too strong. Notice you can almost see the angle structures because that lens is so steep, greater than the critical angle. Here's a child with a progressive myopia. Big, beautiful eyes. They're big and beautiful eyes because this child has glaucoma and has enlarged. Child ended up with about a minus 20 myope because of the enlarging eyes. This child had even worse glaucoma. This is a 55-year-old woman who has had blurry vision since her last eye exam. It's because her entire lens moved forward into the anterior chamber. And when you move a plus lens forward, you get more effective plus power. So that makes the eye too strong. So that creates myopia. Diabetes, cataract. That's right. So there are things that increase the refractive power of the eye, and that's keratoconus as it works on the cornea, lens changes, cataract, diabetes. So these actually change the index of refraction of the lens so that your n prime minus n becomes higher. And then anything that anteriorly dislocates the lens, ROP, those lenses are larger. And then accommodative spasm, increasing the power of the lens. Drugs can do it too. So some drugs, Topamax is one that's notorious for doing that. It causes swelling of the ciliary body, a shift forward of the lens iris, diaphragm, increased plus power inside the eye, which makes the eye more myopic and causes can cause angle closure. And the angle closure in these patients, when that happens, it doesn't respond to peripheral iridectomy because the whole lens iris diaphragm is shoved against the edge of the cornea. So you treat that paradoxically by dilating the patient to get everything to drop backwards. And then things that make the eye too long. So things that make the eye too strong, things that make the eye too long, increasing the axial length, staphyloma or staphylococcus, and congenital glaucoma. A scleral buckle can do it. It's about 3 diopters per millimeter of length, so it doesn't take much. If you tighten up that scleral buckle and lengthen the eye by about 2 millimeters, then you're going to increase the myopia by 6 diopters. And I've seen that exact number not that long ago. Okay, now we've got a patient who's got progressive hyperopia. We need a differential diagnosis there. Why would you have suddenly develop hyperopia in a person? And I'll just say it a little bit slowly. Got hyperopia. Let's give you a chance to think about it. Must be things that make the eye weaker or things that make the eye shorter. CME or central serous retinopathy is what I think you're thinking of. Here's a patient who's got choroidal folds. So this person has choroidal folds and has, yes, a retrobulbar mass. So there could be, so a patient comes in, gets developed increased hyperopia. You look in the retina, and because of that increased hyperopia, you scrutinize a little more carefully and recognize the choroidal folds. You get an imaging study and found that they have a mass behind their eye that's pushing their retina forward and causing the eye to become shorter. And as a result of it being shorter, they're more hyperopic. Here's, we had the answer, central serous retinopathy, and that causes the retina to effectively become shorter because of the fluid under there, and therefore becoming more hyperopic. A lot of times if you've ever tried it in the central serous patient, just try refracting them. A lot of times you'll get their vision quite a lot better. I hadn't thought about hypotonia. That's not on my list. I guess that could make the eye shorter though. So things that make the eye less powerful: lens changes, aphakia, obviously, or anything that pushes the lens backwards would make it less effective and make you more hyperopic. Things that limit accommodation, drugs that affect accommodation, patients with a tonic pupil, third nerve palsy, traumatic third nerve palsy. These are the drugs that can reduce accommodation and potentially cause a hyperopic shift in a latent hyperope. And then things that make the eye shorter. A tumor, like we talked about, pushing the eye forward, central serous retinopathy. Now here's a patient who has, I meant to put my question first, but here's a patient who's had some acquired astigmatism as a result of a pterygium. Again, remember how if you like just step, imagine a foot stepping on the edge of the cornea, it's going to like warp the center of the cornea and cause cylinder. Here's somebody who's got pellucid marginal degeneration superiorly, causing astigmatism. Here's somebody with a posterior lenticonus, which can cause both myopic shift and astigmatism, depending on the nature of the distortion of the irregularity. What are the retinal causes of astigmatism? Is there anything in the retina that can cause astigmatism? I don't necessarily want to look at the answers because it's actually a trick question because there are no retinal causes of astigmatism. When the retina gets warped, you don't get astigmatism, you get distortion because it's all the way back at the secondary focal point of the eye. So you're not going to affect how the light's refracted by the time you get all the way to the retina. So things like epiretinal membrane, those sorts of, anything that warps the retina, it doesn't actually cause astigmatism, it just causes distortion. So there are corneal causes. Chalazion can cause it, a tumor, again, anything that's going to like push on the edge of the cornea, and then pellucid degeneration, teriens, keratoconus. And then there's lenticular astigmatism from posterior lenticonus or lens dislocation, because the lens is, it's steeper on the edge than it is in the center. So if it dislocates and the edge of the lens gets into the pupil, then you'll get astigmatic hair and coloboma. Ciliary tumor can also cause it. So a patient comes in with new onset astigmatism and you have no good answer. You do keratometry, the Ks are stable. So it must be lenticular, but why would the lens suddenly be causing astigmatism? So you investigate and discover a ciliary tumor that's changing the lens shape. So next we move to contact lenses, and we'll talk about clinical evaluation, evaluating the fit, and then we'll get back to that comparing keratometry with refraction one more time. So we'll talk more about the rigid contact lenses, hard lenses, even though we don't use them as much clinically, but in terms of optically, we can better explain some of the concepts that we use. So when we want to fit a patient with rigid contact lenses, we do their refraction, we calculate the keratometry, and then we want to choose a base curve of the lens that's about a half diopter steeper than the lowest K. And the reason is you want to get this, you want this tear lens that is, you need for the contact lens, actually I'm going to switch back to the arrow. You need for the contact lens to be sitting on top of some tears. So that otherwise it becomes uncomfortable although some oxygen comes through the lens, some of it still comes in through the tears. So You choose a base curve that's steeper than the low K, then you convert the refraction to minus cylinder form and zero vertex distance. We'll explain why in a minute. And then you subtract that half a diopter from what's ground into the lens to make up for this little tear lens that's on the surface of the eye. So let's look at an example. You have a patient who has a 13 millimeter vertex distance. Their refraction is plus 11.5 plus 1, and it's 35. Keratometry is what's shown here. What contact lens would you give them? Well, first, we want to choose a base curve that's half diopter steeper than the low K. So that's 44.25 is the lower number. So we want 44.75 as our base curve. Next, we need to convert the refraction to minus cylinder form. So new sphere is old sphere plus old cylinder. 11.5 plus 1 is 12.5. New cylinder, same as the old cylinder, both opposite sign. New axis is 90 degrees away from the old axis. But now we just throw away the minus cylinder. And so we just have a plus 1250 lens. So is that what we prescribe for the patient? No, because we haven't taken away the vertex distance. So we've got to do our 3 steps. Take the reciprocal of 1250, separate 13 millimeters from that, take the reciprocal of the new number, and you get plus 15 diopters. So is that what we'd grind into the lens? No, because we haven't taken the tear lens into account. So you have to subtract the half a diopter of the tear lens, and that gets us to 1450. So for this refraction, you would need a plus 1450 lens to give the patient their best vision. Now, how do you evaluate the fit of these lenses? Well, this is from at least it was in the basic science manual. You want to have the apex clear. You don't want to have apical touch. Like this one, the lens is touching. That's not good. Here's a little video.
And when we fire up this video, you can see that when the patient blinks, the lid pulls the lens up, gravity pulls the lens down away from the lid. Because the lens is coming in contact at 3 and 9 o'clock, it keeps the lens centered along the horizontal axis. And you can see how nicely that lens centers, after each blink. So this is what we would consider a nearly ideal fit.
So you see that pooling, there's tears cushioning the lens. What I was showing here is this is an astigmatic cornea. And so you see how the tears are filling in the steeper part of the cornea. So there's where your minus cylinder has gone. This is why you throw away the minus cylinder, is because the tears themselves provide the minus cylinder for that eye. We call that the Batman sign. This is how you look at the fit of soft lenses. It's a little more it's a little simpler. All you do is you have the patient blink and see if there's some movement. If there's no movement, then the lens is too steep. It's just suction cupped onto the eye. If there's too much movement, then the lens is too flat. It's as if you just have a piece of like saran wrap in the eye that's just moving all over the place. Neither will be comfortable. So there are 2 ways to steepen the lens. So I was going to ask you, what are 2 ways to change the fit of a contact lens? The idea here was to ask you the question right after I've already just given you the answer, as another way to keep you engaged. So the 2 ways to change the fit of a contact lens are to make it to change the size, the curvature, or to change the diameter. And let me show you how that works. So if you have a lens, so say this is a contact lens and we're viewing it from the side. And now we want to, if we cut it here, now that's a bigger diameter. Whereas if we cut the lens here, now it's a smaller diameter. And if you look at the profile of the larger versus the smaller diameter, you see that the smaller diameter just looks flatter. The larger diameter looks steeper. You could take it to, if you made it infinitely small, then you would have a completely flat piece. Whereas if you went all the way out, you'd have a almost, very round piece. So the smaller the diameter, the flatter the fit. The other way you can change it is to change the radius of curvature to make it actually steeper without changing the diameter. So here's a larger radius and here's a shorter radius. And if we take the same diameter out of those two lenses and magnify them, you see that the smaller radius is steeper and the longer radius is flatter. So a patient comes into your office and they've just been fitted with contact lenses and they say the lens is uncomfortable. Their vision is fine, but the lens is uncomfortable. What do you do? It's a soft contact lens. Well, I would sit the patient with the slit lamp and have them blink and look at the movement of the lens. Okay, so you have them blink and the lens movement seems reduced. Doesn't seem to be moving very much. Say, that means the lens is too steep. So I need to change the fit. I need to either make it flatter by decreasing the diameter, or I need to increase the radius of curvature. Or we send the patient for refractive surgery. So we'll talk a little bit about the optical principles of refractive surgery. So the original refractive surgery was radial keratotomy. And the idea there was sort of the opposite of, how I've been talking about how if you step on the cornea in the periphery, then you'll make it steeper in the center. Well, if you destabilize the cornea in the periphery, then you'll flatten the center. And remember, in myopia, the eye is too strong. So we want to reduce the corneal power. If you can flatten it out, then you just make these radial incisions in the periphery of the cornea. It flattens out the cornea, reduces the power, and reduces the myopia. You can also do this more strategically when you have a patient who has astigmatism by doing this astigmatic keratotomies, aka relaxing incisions. So when we do, but that's not used much anymore for good reasons, as we'll talk about. But when we do LASIK or PRK, what we're really doing is it's like we have a lathe and we're cutting a minus lens into the surface of the cornea. So you see that here in panel 6. It's like a minus lens has been dug into the surface of the cornea before the flap is pulled back over. So you, again, trying to reduce the corneal power to make the eye not too strong anymore. And then smile surgery is just another way to do that. And this time, though, the laser cuts out a little lenticle, it cuts out the shape of a plus lens inside the cornea. And then you make yourself a little pathway to get to that lenticle you cut, and reach in with forceps and remove the plus lens that you've created inside of the cornea. By removing the plus lens, it's like you're giving a minus lens. And that is another way to do it. So it's harder to make the eye stronger. I wonder if you could do a minus smile surgery and cut cut a minus lens into the cornea and pull that out. So this is one way, though, is you want to make the cornea steeper. And again, this gets back to this idea of stepping on the edge of the cornea to make it steeper in the front. But instead of putting a foot there, you burn it. You burn little conductive keratoplasty. So you it's like sort of like cauterizing the edge of the cornea all the way around to flatten it out in the periphery so that you get compensatory steepening in the center. Now, refractive surgery can cause some aberrations, and there has been some pushback. It was a little hotter in the literature a few years ago that he has extreme light sensitivity, double vision, visual distortions. His eyes are so dry and sore, he puts drops in every half hour. As far as his LASIK surgeon is concerned, he's a success story. So we do have to think about it. And there's lots of websites and YouTube videos of unhappy LASIK patients, and Dr. Oz.
It's the world's most popular elective surgery, LASIK. It promises your eyesight will go from this to this. But what if LASIK could cause your eyes to see this, or even this? When I heard how life-altering these side effects could be, I needed to know why. So I sent investigative reporter Elizabeth Leamy to go undercover to find out.
I think that was a halo he was trying to. So some of the aberrations that we think about in relation to refractive surgery are caused by some of the basic optical principles that we talked about before, like diffraction. So when you're crossing through any sort of an aperture, including like the RK scars, you can get a starburst around those RK stars. You can get scatter when you have like a hazy flap surface. So then you'll get irregular astigmatism and glare from scatter as a result of that haze that can develop. You can get multifocal lenses, which makes patients have monocular diplopia, monocular triplopia, and this can result, for example, if you had here was a toric ablation, but ended up with a central island, and this caused a multifocal cornea and multiple images for that patient. So there's actually a nice section in the Academy website that I reference here, talking about some of the complications of keratectomy. Another aberration is coma from a decentered ablation, where you have the light sort of streaking out in like a little comet or like a comma from a coma. And then spherical aberration. Our cornea has spherical aberration, but so does our lens and so do the optics of the eye. But it turns out that the spherical aberration in the cornea is complementary to the spherical aberration in the lens. And so overall, the spherical aberration of the eye isn't that bad. But if the ablation takes away that spherical aberration, then you'll unmask the rest of the aberrations in the eye and end up again with halos, and in particular with halos around objects and other forms of distortion. So with the use of customized ablations, which are becoming ever more sophisticated, some of these errors and concerns can be removed, and the goal is ultimately to give people's eyes better than baseline performance, to have eyes performing by removing all the irregularities in the entire optical system to be able to achieve supervision through refractive surgery and customized ablations. So what are the three basic types of IOL formulas? Not just two types. This used to say two types, but now I've made it three types. I'm just pausing to, it's the power of silence to wake you up. Three basic types of IOL power calculation formulas. So there is the empirical formulas, there are the theoretical formulas, And now there are the artificial intelligence formulas. So the empirical formulas are what worked well for many years. The way that works is you operate on like 2,000 people and put in not quite random intraocular lenses, but at the beginning, that's kind of what was done. Everybody kind of got the same power lens. And again, back to the theory, 90% of the time, give everybody a 20 diopter IOL, 90% of the time, they'll be happy. So we make the difference on those last 10%. So, but SRK took those, and then you build up a regression curve and figure out what factors are most important. And those are empirical. Theoretical goes into the optical model of the eye, the schematic eye, and tries to work through the optics at each step. And these depend very much on the effective lens position. The earlier theoretical formulas were way outperformed by SRK, but now the theoretical formulas are now sophisticated enough because they're really good at predicting exactly where the lens is up in the eye. I mean, it's hard. You've heard me emphasizing effective lens power a lot today. It's just hard to underestimate just how important it is. Just a little bit of forward or back on the IOL where it is in the eye changes the power significantly. And now the newest formulas are the artificial intelligence formulas that start with some of this, but that is almost kind of more like empirical, but it's a little bit of a combination of theoretical and empirical, but taking lots of data and letting computers work on it. So here's your basic SRK formula for IOL power. Developed by regression from Saunders, Retzlaff, and Kraft, who studied their results in thousands of patients and found that if you took an A constant, just a fudge factor that's unique for the lens, minus 2.5 times the axial length, minus 0.9 times the keratometry, that was the predicted power of the lens for emmetropia. So all you really need is the A constant for your lens, and that depends on the IOL. It probably has a lot to do with where that lens sits in the eye, among other things. And then 2.5 times the axial length, that actually kind of makes sense because it is about, for every millimeter or so of change in the axial length, in the schematic eye, it's about a 3 diopter change in power. So for this, it's 2.5 for whatever reason, but similar. And then this also makes sense, 0.9 times the K. So for every diopter change in corneal power, you would expect to have about a diopter change in your IOL power. So this is a formula that you can calculate, just write it on the surgical drape during the case if you needed to figure out what power lens you needed for emmetropia. The problem with the SRK formula is it kind of falls apart at the short and the long end of the eyes. So shorter eyes and longer eyes, it doesn't work as well. So they fudged it a bit with the SRK2, but by adding or subtracting from the A constant for shorter or longer eyes. This is something that I found just sort of summarizing the currently available formulas. And this is from the site that's looking at some of the AI approaches to using formulas. And of course, they are saying that they work best for the very shortest eyes and the very longest eyes and for all anterior segment types. But if you wanted to use the AI formula, you can get to the calculator at this website. And it's, I believe that to participate, you put in your data, it tells you what lens to put in. And then after your patient comes back, you put in the post-op refraction. And so then it's one more little click for the AI calculator to be able to come up not just with the IOL power you need, but probably whether or not the patient is going to develop diabetic retinopathy and whether they need, whether they're male or female, and what they had for breakfast. But at least for now, it is a powerful potential change in how we do IOL calculations. So we've made it through part 2. Visual acuity testing, refractive error, accommodation, astigmatism, contacts, refractive surgery, IOLs. You're halfway there to knowing everything you need to know for the next 2 weeks, except, well, I can't really promise that, but trying to keep you here and excited to be here. So let's move on then to other optics of note. Again, we're trying to get more practical here as we go. So we'll talk about magnification, low vision, mirrors, prisms, those sorts of things. And we're halfway through and we're about 3 hours into it. So I think that works about right. So we've got, for magnification telescopes, we're going to talk about the types of magnification: transverse, axial, angular, simple magnifiers, telescopes, magnification effects of refractive correction and anisoconia. And now I'm going to see if you were listening to what I just said. What are the 3 types of magnification? I just said it. By the time I put this question in, it was about 1 o'clock in the morning. So I was feeling a little punchy. So the 3 types of magnification are, see the lag, I don't know if everybody's typing it in or you're all saying like what? Transverse, axial, and angular. See, I had it right here. Emphasize with the laser pointer. So transverse, axial, angular. So transverse magnification brings us all the way back to our U plus D equals V. We never talked about how do you calculate what the magnification is of that image. I mentioned the central ray and ray tracing, you can figure it out that way. But it's actually kind of intuitive. The magnification is the image size divided by the object size. Right? If the image is twice as tall as the object was, then your transverse magnification is 2x. The problem is we don't really know the image size and the object size, but by similar triangles, we know the image distance and the object distance. And so the magnification is just the image distance divided by the object distance. And that we know because image distance is V and object distance is U. Remember U plus P equals V. So V, 1 divided by V is image distance, 1 divided by U is object distance. So if you know U and V, you know magnification. But I like to just say it here as image distance over object distance because that's kind of more intuitive, I think, and maybe a little easier to remember. So the eye, we can talk about magnification in the eye, just remembering the central ray for the eye passes through the nodal point, and we've got that 17 millimeters. And so, again, it's going to be image distance divided by object distance is going to give you the magnification within the eye. Now, because each eye is different, some eyes are longer axial lengths, longer secondary focal points, some are shorter, then it's not a uniform necessarily, but it comes in handy in certain calculations that you'll see later. So that's all on transverse magnification. And then axial magnification is just this one slide. It's magnification along the axis. It's magnification in depth. So axial magnification is the square of transverse magnification. Now the problem is that the magnification at this point is closer to the lens, in this case, is different than the magnification at this point. And so the square of this magnification is going to be different than the square of this magnification. So you get distortion of 3D images as a result of axial magnification being the square of transverse magnification. So in fact, this was the object, was just a little square, but the image is this funny looking thing because of the distortion caused by axial magnification. And it's also, it used to be as wide as it is tall, and now it's quite a lot wider than it is tall. So we'll spend most of our time on angular magnification because that's what's of most relevance when we're using magnifiers, hand magnifiers, when we're using telescopes. Because transverse magnification just doesn't really hack it when you're looking at the moon, because image distance over object distance, but image distance is infinity. So it's kind of hard to kind of work that out when you have to do math with infinity. So we instead ask ourselves when trying to describe something as angular magnification, let's get back to the moon. So we're looking at the moon and we say, oh, the moon is taking up 1 degree of my visual field right now. And so then I say, oh, I'm going to get a telescope and look at the moon. So then you get out your telescope and you say, oh, wow, now the moon is taking up 5 degrees of my visual field. Well, so then you've taken up 5 degrees instead of 1 degree. So that's 5x angular magnification. And the original size of 1 degree of your visual field, when it's off at infinity. So it doesn't matter if you're standing on a ladder or if you're at the top of a skyscraper or the bottom of the skyscraper, it's still going to take up 1 degree of your magnification of your visual field. So the axial magnification is the same. When you start talking about hand magnifiers, it gets a little bit more same concept, but a little more complicated. So we need an extra slide for this. So here we're looking at an object and it's taken up, say, 1 degree of our visual field, but then we look at it through a hand magnifier. How can that magnification be expressed? Well, it's first we'll just look at this arithmetic. We compare, well, no, we're not comparing the size. We're comparing it to the angle that it takes up at a particular distance, because now it matters. So if I'm looking at a nickel on my desk here, if it's taken up 1 degree of my visual field, I don't know if it's 1 degree, but anyway, if I move closer, now it's taken up like 5 degrees of my visual field, but back here it's only 1 degree. So my distance really matters if I'm going to compare it to how it looks when I look at it through a magnifying lens. So we have to set a reference distance, which is arbitrarily set at 25 centimeters. So when we're looking at the magnification of a hand magnifier, it's always with a particular reference distance in mind. And by the way, when you're looking at this nickel through a hand magnifier, notice that the nickel is at the focal point of the hand magnifier. So when you use a hand magnifier and it's just there in front of the, in front of the object, you get when you hold it at the right place, it's parallel rays of light coming towards your eye. So it actually, and you can try it yourself sometime. It doesn't matter if you move further or closer, the image size stays the same when you're looking at it. So the image size through the magnifier stays the same, but when you take away the magnifier, it's dependent on your distance. So all of that is, then we got to do the calculations. We got a theta, tangent, divided by approximately 25, blah, blah. So it's d over 4. So it's the power of the lens in diopters. Again, I guess I need to change that to a p, divided by 4. That's the magnification of a simple hand magnifier. It happens to be, for those of you who want to have that extra burst of knowledge joy, it's d times the reference distance, d times 0.25 meters. And so if somebody tries to change up the reference distance on you to say 40 centimeters, then it would just be d times 0.4 instead of d times 0.25. But that's the power of a simple magnifier. So what that means is that when I look at the nickel through the hand magnifier, then it looks, say the power, say through a 20 diopter lens, so that's 20 over 4 is 5x. Then it's going to look 5 times, it's going to take 5 times as much of my visual field. It's going to be 5 times larger compared with if I take the lens away and position myself 25 centimeters away from the object. So that's the simple magnifier. So when you look at a person's retina through the direct ophthalmoscope, if you're, the only reason there's a dial in the direct ophthalmoscope is to make up for people's refractive errors. But if you're emmetropic, the patient's emmetropic, there's going to be no lens in there. All you're getting all the magnification from that 60 diopters at the front of their eye. So it's like the front of the eye is the simple magnifier, which is at the focal point of the lens. So magnification is D over 4, 60 over 4, or 15x. That means that when you look at the optic nerve through the direct ophthalmoscope, it is 15 times larger than it would look if you cut it out of the back of the eye and held it 25 centimeters away. This is a guy, this is where, you know, I said I like the nerd emoji, but this is me. And I know it doesn't look like me, but it was me. I was going on a ship. We were gonna, I used to work as a longshoreman in Italy, and we were going to be going on this long cruise to work, but there was a big soccer game because you may not know I'm a big soccer fan and player, almost professional, and so we were going to go on this trip, and I discovered that we were going to miss the match. And so we needed to find a hand magnifier we need to find some way to magnify this one tiny little TV so everybody could see it. So this is the story of how that worked out.
Okay, perfect.
Yes. So if we review then we look at this, you see that the television is only taking up 0.75 degrees of our visual field, but once we get the lens at the focal point of the television, now it's taking up 2 degrees of our visual field. So it's 2.6x. And so this porthole window is D over 4 equals 2.6. So it would be, whatever that works out to. Question: what is the difference between a Keplerian or astronomical telescope and a Galilean telescope? Well, we did have some good answers on the types of magnification. Difference between a Keplerian telescope and a Galilean telescope. Just one different lens, just one. Of course, the telescope only has 2 lenses. So let's look first at the astronomical telescope. So the idea of a telescope is it's sort of like a lever, like a physical, but instead of a lever to give you a long side of the lever to give a lot of force on the other side, it's like there's a long side to give a lot of magnification. So you take a parallel rays of light coming from the moon, or better be from the moon than from the sun. And so we don't want to be burning our retinas out. So they're coming from the moon, parallel rays of light. We have a plus lens, and that converts, so then the light converges. It reaches a point where it forms an image, then it starts diverging again. We draw it like this for just for fun. So then it diverges again, but now we want to get it back into being parallel rays of light again so we can focus on it. So you take another plus lens, and now parallel rays of light coming out again. Now, if these lenses were both the same power, then the intermediate image plane would be right in the middle, so you'd have no magnification. But if one lens is a lot more powerful than the other, then the magnification is the difference in the focal lengths of the two lenses. So it's the focal length of the objective lens divided by the focal length of the eye. But since focal length is reciprocal of power, it's the power of this magnifying telescope is the power of the eyepiece over the power of the objective. And so you'll see that this telescope has to be as long as the two focal lengths put together. And you can do this. Next time you're in the office, just pull open the drawer that has tri lenses in it, and get like a plus 20 and a plus 10 and hold them. And you'll see you can make yourself a little telescope. So now the thing about it is, though, if we follow this upper ray, the upper ray ends up on the bottom and the lower ray ends up on the top. And so the image is inverted. So how is a Galilean telescope different? Well, Galileo had this better idea that instead of using two plus lenses, you switch the eyepiece out for a minus lens. And so if you've got a minus lens, now you still have parallel rays coming in, they're still converging, but now you put the minus lens in before they've had a chance to form the intermediate image plane, and then you convert them back to parallel rays of light. So there's two advantages to this. One is that now the focal lengths are overlapping, so the telescope is shorter. And the other is that the bottom rays stay on the bottom, and the top rays stay on the top. And so the image is upright. But the magnification is exactly the same. It's the power of the eyepiece over the power of the objective. So whether it's Galilean or Keplerian, the telescope is still power of the eyepiece over power of the objective. So surgical loops are just telescopes, but then they have an add on the front because we don't want to be operating on infinity. So imagine put a +3 add on there, then you got a 33 centimeter working distance, So why are these so different? Well, this one is a Galilean telescope, and this one is an astronomical telescope. And the astronomical telescope would give an inverted image, which would make it really hard to operate. And so it has inverting prisms in it too. So it's heavier. So it's quite a lot heavier. It's harder to get the image just right. But the reason that I like it is that there's less, I find that there's less distortion and you get a broader field of view. So it's a wider field of view, it's less distortion. I think there's more light. It's just higher maintenance. So it's like the Toyota and the Ferrari. The Ferrari, it's higher maintenance, but you get the performance out of it. Question. What is the magnification of the following lens combinations? A +20 lens used as a simple magnifier. Well, here's another one I already told you. It's D over 4. 20 over 4 is 5x. How about, assuming a reference distance of 25 centimeters, how about a minus 20 plus 4 telescope? Well, it depends on which one's the eyepiece, but if we assume that the minus 20 is the eyepiece, then it's 20 over 4 again, or 5x when the 20 lens is the eyepiece. If you flip it around, it's if you flip it around, it's going to be 1/5 x. So I remember doing that when I was little, just looking backwards through the telescope. It's like, ooh, everything's smaller. What about a plus 20 plus 5 telescope? That's going to be 20 over 5 for 4x, again, assuming the 20 is the eyepiece, a 4x telescope. How else are these two telescopes different? The number 2 is Galilean, so it's going to have an upright image. This one's going to be an inverted image. The number 2 is a Galilean telescope, so it's going to be short. It's going to be the difference between those focal lengths. This one's going to be a longer telescope, the sum of the two focal lengths. So, when you correct aphakia, you also create magnification. And it's quite a lot, actually. With an IOL, it's hardly anything. There actually is some magnification, even when you use an IOL, because it's not exactly in the same place as the natural lens. It's a little bit further forward. A contact lens is 6% enlarged. A spectacle lens is 25% enlarged. So it's really hard to be binocular when you've got like a plus 10 lens over one aphakic eye and no lens over the other phakic eye. So, excuse me, but even ordinary lenses change retinal image size. And so you get 2% per diopter of power at a 12 millimeter vertex distance. So I think my glasses are around -4. So I've got 4 times 2%. So that's 8% of minification of all of you who I can't see. So plus lenses magnify, minus lenses minify. Because it's actually like you've got a little Galilean telescope in there. So that is, when you take somebody's lens out, their natural lens out, it's like you're putting a -15 lens inside their eye. So that's the eyepiece. And then you've got to correct that with like a +10 spectacle lens. So then it's like a -10 eyepiece and a +10 spectacle lens. So power of the eyepiece over power of the objective is going to be 15 over 10 or 1.5x, which is 50% bigger. All right, so question. What is anisoconia? I think I have a second question here. Assuming we know what anisoconia is, I'll just give you a minute to think about what is anisoconia. And it has nothing to do with anise, the spice, or the seasoning. How much anisoconia can be tolerated by an average person? See, 2%, 5%, 25% difference between images by your average person. Kids can tolerate more, by the way. So you should never worry about giving a kid like whatever they need. I mean, maybe not an aphakic, unilateral aphakic, but short of that. So anisoconia is an image size difference between the eyes, and up to 6 to 7% can be tolerated in most people. Remember, it's 2% per diopter, so that's 3 to 4 diopters of spherical difference between eyes is generally tolerated. So, for example, if you had a patient who used to be -3 in both sides and you do cataract surgery and you made a little miscalculation on the left side, and they end up with 1 diopter of hyperopia in their left eye. Now their left eye is going to be 1 times 2 is 2% larger, but their right eye is going to be 3 times 2, 6% smaller. And so the difference here is 0.94 is 6% smaller, 1.02 is 2% larger. So it's 8% difference. That's right on the borderline of what they might actually be able to tolerate. They may end up with double vision as a result of having the image size too much of a difference in image size. So you could correct that. You could correct it by simply putting the -3 contact lens in the right eye and +1 on the left eye. But another way to do it, if you wanted to have the two exactly the same, is you could actually put a -4 contact lens in the right eye, and then the glasses would both be +1. So then you'd have pretty much equal, and then there'd be 0 anisoconia. So if you wanted to zero out the anisoconia, which you wouldn't have to do, but let's say you wanted to, you do that with a -4 lens, so that then the spectacles would both be +1. All right, so that's anisoconia. Let's move on now to low vision, and you see where we are here. We're low vision, mirrors, prisms, and then we'll be to part 4. So for low vision, a lot of this just has to do with, they're older patients, a lot of them, not all of them. We have a lot of not so older patients at Boston Children's Hospital, who we have a low vision service there. But anyway, I digress. A lot of the elderly patients, they're not going to have time to be thinking about a lot of things. You want to know, what do they most want? Is it they want to read? Is it that they need to find the bus on the way to wherever they're going? So just talking to the patient is something that we do. And then what can we offer them? Near aids, distance aids, and non-optical approaches. So we'll talk about those. First, a question. What is the definition of legal blindness in the United States? I know we have someone here from the Philippines who has their own definition of legal blindness. Same with Albania. Same with, I'm just looking at the list here. Yes, Dr. Yap from the Philippines. We don't know what his definition, but for those of us who are taking the US boards, I think we're supposed to know. So it is 20, 200 or worse, best corrected vision in the better eye, and the field of vision in the better eye is 20 degrees or less. So it's both a visual field criteria and a best corrected visual acuity. So when people say they're legally blind in one eye, that's just for dramatic effect, because it's the best corrected vision in your better eye. And best corrected. That does not vary by state. Now, driver's license requirements do vary. So, Massachusetts versus Rhode Island versus California, they may have different requirements for what you need to drive, but federal definition of legal blindness is there. So when we're doing low vision assessment, we need to first get a visual acuity, and just saying hand motion or count fingers is kind of not a very great place to start. So if we can start with a number, so there are these low vision visual acuity cards is one way to do it. This is a 2700 number. Kind of a clue with the number 7 there, then of course you can also just move the patient closer to the eye chart. And so we do that. Now our eye lanes are not 20 feet, as many aren't, but so what I do is I walk the patient halfway. So if it's 14 feet from the eye chart, I'll count ceiling tiles, which are 2 feet each, and I'll count them out until they're 7 feet away. And then I can double those numbers off of the eye chart, or I can go to, a quarter of that and quadruple those numbers from what they're seeing. So then for near aids, we have plus lenses, loops, electronic displays, and non-optical aids. So let's talk about first about plus lenses. But before that, we have a question. What is Kestenbaum's rule? What is Kestenbaum's rule? That wasn't in the 2020 version of this lecture. I decided to put it back in just so I could ask this question. There's a lot of Kestenbaum things floating around. So Kestenbaum's rule is when you have a patient with low vision and you want them to be able to read newsprint comfortably, then what you do is you take their visual acuity and take the reciprocal, and that number in diopters should give comfortable reading of newsprint size fonts. So if they have 20/100 vision, the reciprocal of that is 100 over 20 is 5. So you would give them a 5 diopter add if they wanted to read newsprint comfortably. Now, if you give them a 5 diopter add, how far away are they going to have to hold the newspaper? Take another reciprocal. 1 over 5 is 0.2 meters or 20 centimeters away. So they'll be holding their, maybe I should change this example to if they want to read their phone, 20 centimeters away in order to be able to read that. So that's the problem with, you can use plus lenses, you can use a high add of up to 20 diopters. And so she's wearing, Dr. Baglieri here is wearing the 20 diopter lens. And so she has to be 5 centimeters away to be able to read. The good thing is it gives a wide field of view. It leaves both hands free. So lighting isn't usually too much of a problem. But she's got can be uncomfortably close. And, if both eyes have decent vision, you've got to converge a lot to be able to see. So for the convergence problem, there are lenses for reading that have the high power and that have some base-in prism for the exotropia that you will inevitably experience by having to hold things 5 centimeters away for a long time while you're reading. The alternative to the high add is in the bifocal or high power single vision lenses is a handheld magnifier. And those also come generally in 5 to 20 diopters, which using the magnifying formula, D over 4 is 1.25 to 5x. And so, someone did get the answer right on the Kestenbaum. You see the advantage here is now he's got a variable eye to lens distance. Because remember I said, if you hold this magnifier at the focal length, then it's parallel rays of light coming out. So he can be as close or as far away as he wants to while using this. The problem is that it does require more dexterity. So he's got to have a steady hand here. And the lighting can be a problem as well. I mean, he had to take this map outside just to get enough light to be able to see with that little magnifier. So to get around the dexterity part of it, there are also stand magnifiers that also come in. They actually come even up to 50 diopters of power, and that's the one on a stand. Here's like a bubble style stand magnifier, and you see the amount of magnification you get compared to the other line. And then they have special features like built-in lighting, a reading line that can help. And you see the difference there between the lower and the higher power magnifier. You get more magnification, but the higher you go with the mag, the smaller your field of view is going to be as well. But the lighting helps, and if it's it can be useful. So, a question: what are the relative advantages of the two main types of plus lens near aids. Again, I just told you so, but I just want you to think it through. You know, it's like oral exam. I'm giving you your oral exam. Doctor, what are the relative advantages of the two main types of plus lens near aids? So I should have had my necktie on though. And I should have a virtual hotel room background. Or actually, I guess the boards are virtual now. But I digress. Well, so we'll just remind you the high plus ads give wider field of view, leave both hands free, but have a restricted field of view. The handheld magnifiers require more dexterity, have a smaller field of view, but allow for variable eye to lens distance that many people find more comfortable. So probably your average person who needs a low vision aid, you're more likely that they're carrying a handheld magnifier in their pocket than that they have like 20 diopter by reading glasses. So near, that was good. We got a good answer on that. So near vision aids, we also have loops. So just as we have surgical loops, there are reading loops. So the good thing about the loops is that they allow for more of a distance away from the object of regard. However, their field of view can be smaller, and they're very unforgiving, as anyone who's used loops knows. If you get a little too close or a little too far, it all goes out of focus. So, and they're funny looking. So not that many people, I mean, it's not that common to see people using these sorts of reading loops, but they are out there and, you know, for use at home. And then there's CCTV readers, so electronic displays. These allow for reversing contrast for large amounts of magnification. But you see that he needs to have a certain amount of dexterity. You've got to be able to translate from what's happening on the page to what's happening in front of you. So computer scanners get past a lot of that. Then you just put the device in the scanner and it reads for you. And you know, our phones are becoming more adept just having built-in features that you can take a picture and have it read to you whatever's in the picture. And then we don't want to forget about non-optical aids, which patients can find very helpful: large numeral telephone dials, large print crosswords, signature guides, playing cards. And the positioning of lighting is also important. This is something just entertaining about this to watch. I don't know.
No more than a 60-watt bulb is needed to provide enough illumination.
So,
the closer the light is to the page, the brighter the illumination.
Like he's not paying attention.
It is also important to place the light below the eye level and direct it away from the face to avoid glare into the eyes. When using a magnifier with the light must be placed below the magnifying lens to avoid glare off the task.
So,
no
anyway,
more than a 60-watt bulb is needed.
A lot can be done with light to help patients. Now, for distance aids, the available options are less. Maybe the demands are somewhat less, but some people want to be able to drive, and there are these bioptic lenses that can be used legally for driving in some states, which sounds a little scary, but the idea is your peripheral vision is 2400 anyway, and so what this does is this is two different designs, helps you to read the road signs. Other kinds of telescopes that can be available, they can have adjustable focus. And then there's absorptive lenses. Just as lighting is helpful for reading, absorptive lenses can be helpful for glare control or for dark adaptation for patients who need that. And then there are electronic aids, which do seem to be expanding in their capability. This is one that I found 2 years ago from Iris Vision. Now I found this last night. They have like a more sleek looking version. And here's how this works.
This video shows how Iris Vision works and how to control its many functions. As an example, we can take iris vision out into the real world to see how the device performs in a typical supermarket. The telescope can be trained at the center of the visual field, on any item in the vegetable stand or on any price tag. It can be magnified or decreased to examine items in great detail to make it easier and more readable to the patient. The touchpad on the iris vision device helps patients have more control over their view.
So, even this probably may not be so socially acceptable, but now we're getting a little bit closer to something that people might be comfortable wearing in public, maybe. And then there's implantable mini telescopes. So we have a little video here of Samuel Maskett implanting a telescope into the eye of a low vision patient. The idea there being to give even further magnification. Now, my quibble with these telescopes, and I don't know all the specifics, but the other way to give lots of magnification would be to just leave the patient aphakic and give them plus 10 or plus 12 spectacles, because then you'll get, that 50% magnification or more. So something to consider before you put a telescope in somebody's eye. Now we'll move on to mirrors. And so we'll talk about the different types of mirrors, plane, concave, convex, astigmatic, Virgin's calculations, and back to this question of real and virtual mirror images. So mirrors are just lenses, but they flip over the image space. Actually, you know what? It's 12 o'clock here in Boston. Why don't we take another, just a little 5-minute break here? So I'm going to try to give us a break again. So it wasn't a disaster last time. So we're going to stop the live stream, and I'll see you just 5 minutes. See you then. Okay, well, I think we're back. Except I've got an ad going. Okay, there we go. And make sure I'm not muted. All right, welcome back, everybody. Thank you for the comment about free wisdom. I did, since I have more than 1,000 subscribers, I was allowed to monetize my channel. So I think I've received something like $8 so far in the last, since I was able to start monetizing about 6 months ago. So it's not entirely free. So mirrors. We will talk about the different types. So as I said before we left, they're lenses that flip over the image space, and they are reversing the direction of light. So they really act like lenses, and all the calculations we did work like lenses. So there's convex mirrors that add minus vergence, and concave mirrors that add plus vergence, and plane mirrors that add no vergence. Oh, we're starting off already with a question. How much of a full-length mirror is actually needed to allow a person to view their entire body in the reflection? So to think about this, we want to think about, well, where is the light coming from that needs to get to the eye, and what path does it follow? And so here's a person on the left. Here's the mirror. This is their image on the other side of the mirror. And so if you imagine the light is going to be from the foot, which is as low down as they're going to look, is going to come about halfway up the mirror before coming to the eye. So you really only need about half of the mirror to see your whole self in a plane mirror. The plane mirror, this is Dr. West here took some pictures to show some of the features of a plane mirror. For one thing, no matter whether you're far away or close up, the image is always upright in a plane mirror. What you can't see is that the object, the image is as far away from the mirror as the object is in front. But what that translates to is that the field of view of the plane mirror never changes, no matter how close or far away you are. Here you see a little bit above the head, but here you see a little bit below the neck. The total field of view is exactly the same for a plane mirror, whether you're close up or far away. Contrast that with a concave mirror, where when you're far away, now the image is inverted and minified, whereas when you're close up, the image is upright and magnified. So very different compared to the plane mirror. And then what about an astigmatic mirror? Well, it's kind of hard to find an astigmatic mirror. Oh, sorry, here's a convex mirror. So in a convex mirror, the image is going to always be upright and minified. And it even says it right on the mirror that they are minified. Objects in mirror are closer than they appear. That means they're minified. And then astigmatic mirror, as I say, there aren't many in the world, but there are cylinders in the world, and some of them are reflective, including this oil tanker, or maybe it's a milk tanker, I don't know. But you see on the long axis where there's no, where it's flat, there's no magnification. But on the vertical meridian, you've got minification in this case on the plus side. Well, the convex, it's because it's like convex mirror. So how do we do our U plus P equals V calculations? Well, sort of like we do for anything else. So here's an object. It's 25 centimeters from a mirror. So where is the image? Well, we start at the object. We know we're 25 centimeters away, so we take a reciprocal. 1 over 0.25 centimeters is 4 diopters, so it's diverging light that comes up to the mirror. And so U plus D equals V, so -4 plus 0 is -4. Now when the mirror, the light bounces off the mirror though, but it bounces off with a divergence of -4. So it's -4. So where's the image? Well, we can keep going to the left here. The rays of light are going to keep diverging. So we have to create imaginary extensions of the rays of light back to a point of intersection somewhere to the right of the mirror, somewhere behind the mirror. How far away is it? Take a reciprocal. 1 over 4 diopters is 0.25 meters or 25 centimeters. So as I said, the image is as far behind the mirror as the object is in front. Now, mirrors are curved surfaces. They refract light, and so we need to be able to calculate their power. Now, remember how the refracting power of a surface was n prime minus n over r, where n prime minus n is the difference in refractive index between substances. But in a mirror, there's no n prime and n. It's just bouncing off the mirror, so it's always staying the same. But what happens is n prime becomes 1 and n becomes -1, so 1 minus -1 is 2. So it secretly is n prime minus n over r, but because it's a mirror, n prime minus n turns into 2. It also happens to be, so it's 2 over r. 2 divided by the radius of curvature of the mirror is the power. Just to back up though, the power is also the reciprocal of the focal length, right? So it's going to be 1 over the focal length of the mirror. Focal length is half the radius of curvature. So you see here, here's the center of curvature. Here's the radius of curvature. And here's the focal length. What's the focal length again? Oh, that was one I had you answer. It was, it's where the parallel rays of light come into focus. So secondary focal point. So 2 divided by r, 2 over radius of curvature is the reflecting power, which is the reciprocal of the focal length. A question, does the central ray of a mirror go through the center of the mirror? And if not, what does the central ray pass through? So is this an accurate diagram of central ray for this mirror? Giving you a minute to think about that. Well, I will tell you that it is not correct. The correct central ray passes through the center of curvature of the mirror. That is correct. And that matters when you're thinking about images and objects being upright and inverted. So there's a central ray. So then we have an object. We do our U plus D equals V, and we know that the tip of the image is going to be somewhere on the central ray for this mirror. So if it happens to place it here, if U plus D equals V happens to place the image here, then we know the image will be inverted and minified, like in the first picture of the concave mirror far away that Dr. West showed. How about a convex mirror? Well, the center of curvature passes through the central ray passes through the center of curvature again. So it's always going to be, the image is always going to be behind the mirror. So it's always going to be upright and inverted. And then what about a concave mirror? This is where it can get kind of interesting. So here's a 4 diopter shaving mirror. Let's do a Virgin's calculation. So it's a 4 diopter shaving mirror. So first thing is we got to figure out what's the power, or where's the center of curvature, or where's the radius of curvature of the mirror. So D equals 2 over R, right? So if D is 4, so 4 equals 2 over R, so R must be 0.5 meters or 50 centimeters. So the center of curvature is 50 centimeters away. We've already said that the object is 16.7 centimeters away. And so we need to calculate the divergence entering the lens. So it's going to be, we got to take a reciprocal. 1 over 0.167 centimeters is 6 diopters from our reciprocal chart that we all memorized earlier this morning. So U entering the mirror is minus 6 diopters. We just said it's a 4 diopter shaving mirror. So U plus D P equals V. So negative 6 plus 4 is negative 2. So the light bounces off the mirror with a divergence of minus 2. So it's diverging light. So where's the image? Well, we have to create imaginary extensions of the rays of light back to a point of intersection somewhere behind the mirror. How far away is it? Take a reciprocal. 1 over 2 diopters is 0.5 meters or 50 centimeters. So it's 50 centimeters away. And you can tell by how I'm angling this. We draw the central ray to figure out if it's upright or inverted. There we go, 50 centimeters. Does the central ray go from the tip of the object through the center of the mirror? No, it goes from the tip of the object through the center of curvature of the mirror. So there's our central ray. So now we know the image is upright and magnified, and that's why this mirror is useful for shaving. It's a virtual image because it's on the opposite side of the rays that define it. And so for the most part, all plane mirrors, all convex mirrors are going to have virtual images that are behind the rays that define it, on the opposite side of the rays that define it. There is one circumstance where you can get real images, and that's in a concave mirror, but only if the object and image are in a particular configuration, such that you have positive divergence exiting after you bounce off the mirror. So either the real object and real image can be configured like this, or if you put an object here closer to the mirror, then you can have a real image that's a little further out from the mirror. So we can play games with these concave, since you can create real images, you can play some games with it that you can't play with virtual images. So here's one example, the disappearing light, phantom light bulb. So how is that working? You see there's a concave mirror there, so that's suspicious. So there's the light bulb creating a real image on top of the, so that must be, so it's at just the right distance that we get an image of the light, a real image of the light bulb up above. And even if you were physically there in 3D and seeing this, it would appear to you that this mirror, that this light bulb was in that socket. Now, we can also use the surface of the cornea is a convex mirror, and we can use that to identify the reflecting power of the, to identify the position of the corneal light reflex. Actually, we have to, this is out of sequence, so now I've got to ask. Kind of gave you the answer here. Optically speaking, is the corneal light reflex on the cornea, in front of it, or behind it? In front of it, behind it, on it? Just seeing if anybody has any thoughts. I already just showed it to you, but I skipped by it. Tried to skip by it quickly, but I just said that any convex mirror is going to, the image is going to be behind it, right? So it's going to be a virtual image behind it. So that is true of the cornea too. So if here's the corneal light reflex comes out of the hand light, it's diverging light coming out of the hand light 33 centimeters away. So U equals -3. The reflecting power of the cornea is 2 over R, 2 divided by radius of curvature. If we say the radius, I know this morning we said it was 7 millimeters, but for this example, we're going to say it's 8 millimeters. So if we say the radius of the curvature of the cornea is 8 millimeters, then the power of the cornea is 2 over R, or 2 over 0.008, or 250 diopters, or it's really -250 because it's adding minus vergence. Now, some of you are saying, wait a minute, you just said this morning that the cornea has a power of 50 diopters, not 250. Like, this is way different. But when we were talking about it this morning, that was the refracting power of the cornea. That's what the light that gets through the cornea sees. This is the reflecting power. This is what the light that bounces off of the cornea sees. So the reflecting power of the cornea is 250 diopters. So U plus P equals V. -3 plus -250 is -253. So the light bouncing off of the cornea has a vergence of -253 diopters. So the corneal light reflex is going to be somewhere behind those rays of light, an imaginary extension of the rays of light, back to a point of intersection, somewhere behind the cornea. How far away is it? Take a reciprocal, 1 over 253 diopters is 0.004 meters, or 4 millimeters behind the corneal surface. So it's 4 millimeters behind, which actually is even behind the iris. So again, optically speaking, when we're looking at his corneal light reflex, that's actually behind his iris, 4 millimeters behind the surface of the cornea. That's what makes the Krimsky measurements sort of hard to gauge or judge, because if the corneal light reflex was like right on the surface of the cornea, it would be easier to judge the angle of strabismus looking at the corneal light reflex. But because it's back here, like if it was in the very center, it wouldn't move at all. So it only moves like half as much as you would expect. So it's just hard to judge how deviated the eye is just looking at the corneal light reflex. So next we'll jump to prisms. And prisms are optical devices that bend light towards the base. So they bend to the base. So you can think of the light as being sort of draped over the prism. And that is because when you go from low to high refractive index, you're bent towards the normal to the interface. And then when you go from high to low refractive index, you're bent away from the normal to the interface. And so on the whole, you end up, as I say, directing the light towards the base because of the shape of the prism. So the prism power depends on the angle of incidence. Oh, this is the picture I used to promote the lecture. So you see how these prisms, these are both 25 prism diopter prisms. One stacked right on top of the other. They're both 25s, but this one's at a greater angle than this one. So you get more prism power, you get more deflection of the image. So the position of minimum deviation is where the angle of light coming in equals the angle coming out. Anything else, you get a bigger angle. And here you can see it in real life. You see that position of minimum deviation, there is the position of minimum deviation. Anywhere else, you get even more deflection of the image towards the apex. So we want to try to do our measurements, our strabismus measurements with the prism in the position of minimum deviation, which is equivalent to placing it in the patient's frontal plane. So the angle in equals the angle out. And so in the plastic prisms that we use in the clinic are calibrated to the position of minimum deviation. So that's why we want this in the frontal plane. Anything other than that, and you may end up neutralizing more than you realize you're neutralizing. Now, some clinics have glass prisms. You can tell because they usually have some chips in them. In that case, those are calibrated to be perpendicular to the visual axis. So they would be held differently, but it's not, at least in the US, I don't think they're anywhere to be found. So this person is having their strabismus measured. This is the correct way to hold the prism. This is in the Prentice position, which is not what we want unless we have a glass prism. Now, if you combine prisms, they don't necessarily add up. And in fact, in this case, we've combined a 30 with a 50, I think. And what you're getting is you don't see the eye at all. You're getting total internal reflection. So when you stack prisms, you can't stack them two horizontal prisms touching each other like that because you change the nature of the second prism. I'll show you how that works. So here's two stacked prisms. And remember, the position of minimum deviation, the angle in equals the angle out. But if we zoom into this part where they're stacked, well, the angle out, that's fine. It's leaving at a certain angle. But now the angle in is anything but the position of minimum deviation. So you get way more prism power out of prism B than you think when they're stacked like that. So to work around that, if you need more than one prism over one eye, then then what you can do is hold the prisms like this. So then you put your thumb on the bottom and one finger on the top of each. And now we've got both prisms in the position of minimum deviation, and then 40 plus 5 gives you the 45. The other way to combine prisms, though, is just simply to put one over each eye. And so that's what's being done here. And now you don't, they're both in the frontal plane, and now you don't have to worry about stacking and all and the errors that brings about. But is 50 plus 25 equal to 75 prism diopters? Well, what is a prism diopter anyway? I know I just asked that as a question, so you're expecting to see the gritted teeth emoji asking you to think about it. But I'm just going to tell you what a prism diopter is. I'm feeling generous. So to calibrate a laser pointer, so to calibrate a prism to determine how much power it is, you take a laser pointer and you shine it against a wall. This is a brand new slide, and another reason I was up late last night, so I'm very proud of this slide. So I'm going to make you see it more than once. So you shine the laser pointer at the wall, and now you take a prism and you put it in the path of the laser pointer, but you have to put it 100 centimeters or 1 meter away from the wall. And now in comes the prism, and watch this. Here it comes. Oh, and the light just deflected toward the base. Now, how far down did it move down the wall? Well, maybe I shouldn't use a prism for this. A laser for this. I'll confuse you. Well, let's say that it moved 15 centimeters down the wall. Well, then that means we have a 15 prism diopter prism. So that is the definition of a prism diopter. So we're going to do that one more time so that I get my joy out of this slide. Laser pointer, 100 centimeters away. We put in a prism. It deflects the light toward the base. 15 centimeters. That means it's a 15 prism diopter prism. So in the world of optics so far, I've always been bringing it back to meters, right? Before we do any calculation, we bring it back to meters. Prisms are the one exception. In prisms, when we do our calculations of prism stuff, we do it in centimeters, as you'll see. So here's a simple question. We know 1 plus 1 is 2. What's 100 prism diopters plus 100 prism diopters equal? Dare I say 200 prism diopters? But wait, he wouldn't be just asking it if the answer was 200 prism diopters. It must be something else. Well, it is something else. Prism diopters are not linear. So for example, a 45-degree angle equals 100 prism diopters, right? Because 45 degrees, you're 100 centimeters away, but it's a 45-degree angle. So this is a right triangle. So this is going to be 100 centimeters down. Okay, so a 90-degree angle, well, where does the laser pointer hit the wall if this is taking a 90-degree turn? Never. It goes to infinity and beyond. So a 90-degree angle is infinite prism diopters. So 100 plus 100 prism diopters equals infinite prism diopters. Here's the chart of prism diopter. And on average, it's about 2 prism diopters per degree for most of the range that we would ever be measuring strabismus. So, who operates on 173 prism diopter deviation? Well, I do, but not that many people do. And I get very upset if the orthoptist says it was 171 prism diopters. And I'm like, how am I supposed to fix this patient? If it's 173 prism diopters, I need to know that. Like, I can't just operate on 171 prism diopters and expect to get a good result. So it can be very hard to work for, but I care for my patients. So to so what we do though is this 2 prism diopter per degree comes in handy because patients don't know what prism diopters are, but they know what degrees are. So we can say, for example, well, before surgery, you had a 30 prism diopter misalignment, but now, thanks to the operation, we've reduced it to 15 degrees. Now, we may be thinking about doing an enhancement down the road. So, as we've seen, images are, light is displaced towards the base, right? Light is displaced towards the base in a prism. So, but I'm going to show you a little trick, a little thing that might be counterintuitive. So if this is a prism, it's base down, we're going to put it in front of this projector. And so if light is displaced toward the base, we should see the image of the eye chart move down on the screen. So let's see what happens. Okay, here we go, base down. Yep, moves down on the screen. Now we're going to put it in front of our own eyes. Whoa, it went up. How could that be? It moves down when we put it in front of the projector, but it moves up when we put it in front of our own eyes. And that's because this is the real image that we see, but this is a virtual image of the eye chart of the projector. So, and that's what this diagram shows. So here is the light being displaced toward the base. So the image just goes down as you would expect. Here is our eye looking through the prism at the image. So the light of that coming out of that, square on the screen, it goes through the prism and is deflected toward our eye. And so we create imaginary extensions of the rays of light and expect that the stuff that's down there is actually straight in front of us. So a virtual image is displaced toward the apex and a real image is displaced toward the base. So, a question, and I tried to make it easier by giving you a one-eyed patient. If a prism is placed base up over one eye of an orthophoric person, he's always orthophoric, would they experience a right hypertropia or a hypertropia or a hypotropia? We're not even saying right. Would they experience a hypertropia or a hypotropia if we place a base up prism over the right eye? I keep saying, that's to give you time to think, because maybe I'm pretending like I don't know the answer, or maybe I actually don't know the answer and have to think it all through. So the answer is it's a right hypertropia, or it's a hypertropia. So the way that I think of this is, I'm going to get my laser pointer back. My permanent laser pointer, now that I'm facile in this. Imagine that there's a person inside of his eye who's holding a laser pointer. And that laser pointer, the light's going to come out of that and it's going to hit this prism and it's going to get deflected toward the base, which means it's going to go up like that. And so his right eye, or his eye, is looking higher than it should be. So he ends up with a hypertropia by putting a base up prism over the right eye. Another way you can think of it is, how would you fix that? You'd fix it with a base down prism. And we know from our clinical experience that base down prism over the right eye would treat a right hypertropia. No, he only has one eye again. So there's another way, which is just to look at the image. So I've been saving that, and now I'm going to show you what it looks like. So here's an orthotropic person. And we're going to put a base up prism over his right eye. Now, you see a couple of things. One is, you see the whole image of the orbit has actually moved towards the apex of the prism. So it almost looks like it's a hypotropia, but it isn't. That's just the orbit that's shifted down. Look at the corneal light reflex. Notice that the corneal light reflex is displaced downward within the pupil, meaning which is consistent with him having a right hypertropia. So 3 ways to emphasize that putting a base up prism over the right eye is going to give you a right hypertropia. 1, you can see it. Look at the corneal light reflex. 2, if you've ever done any prism coverage measurements yourself, you know that you would correct this with a base down prism, and a base down prism treats a right hypertropia. And 3, the one that works best for me is, I imagine that there's someone inside of the eye pointing a laser out of it, and I see that it's displaced up toward the base of the prism, and therefore it has to be a right hypertropia. Now, I've gotten into like almost shouting matches with people who try to say the opposite, because they get confused by thinking about that the eye is going to like, now it's hyper, so it's going to move down. And so they just start confusing themselves, thinking that the hyper eye has moved down, and so it's hypo or something. So just try not to think about, just imagine this person has no fusional vergence whatsoever. He can't deal with it. He's just seeing double. He's got a right hyper. Now, prisms aren't the only place that we have prisms in ophthalmology. We also have prisms in ordinary spectacle lenses. And remember Prentice's rule? Wasn't that the #1 question you're likely to be asked about on the board exams? Isn't that what I said? I think so. So we probably ought to pay attention to this one. So Prentice's rule tells us what is the prismatic power of a lens when we get away from the optical center. So right in the optical center, there's no prism power. Great. But as we move away, and you can see that there's prism power, sort of, like it almost looks like a prism. It looks like a base down prism here. And so the deflection, though, it's delta, the prism power generated, equals h, the distance away from the center of the lens, in centimeters, times d, the power of the lens, in diopters. And by the way, this is one reason I think that we try to refer to prism power in prism diopters and lens power in diopters, because it could allow for confusion to happen. So you can call it 10 prism diopters, you can call it 10 prisms, but don't call a 10 prism diopter prism a 10 diopter prism. It can confuse people, especially me. So delta equals h times d. So it's, and so that's like the formula that you like need to remember and know how to use. So we'll give you an example of where you can do that. And you know, I said the plus lens looks like is what it looks like. It looks like 2 prisms base to base, whereas a minus lens, you use your imagination, it looks like 2 prisms apex to apex. So you can actually tell if somebody's wearing minus or plus lenses by looking for that prismatic effect in addition to the minification effect. So this person looks like it's prisms base apex to apex because the image is displaced toward the apex, so it's coming in. So that must be a minus lens. Whereas this person, now you see it's hard to even tell. It's kind of a strong lens, but it's deflected the opposite way. And so that's like base to base, the image is displaced toward the apex. And so that's how you know it's a plus lens. Now you can get prismatic power also vertical by if lenses are bent or damaged, if the frames are damaged. And I think I told this story in the 2020, so maybe even the 2010. But it's a good one because my wife, Dr. West, tells the story of how she was called to the emergency room to clear the eye because they were taking a patient to was plastic surgery, was taking a patient to the OR for an orbital fracture. The patient was experiencing diplopia. And so she went to clear the eye, make sure there was no holes in the eye. And the patient was seeing double and his glasses looked kind of like this. And she took off the glasses and bent the little arm back in place and put them back on, and the double vision went away. So she cleared the eye and took away the case. Now, plus lenses magnify the eyes, as you can see. They also magnify the appearance of any strabismus that might be present. But what do they do to the strabismic deviation? That is, what is the effect of a plus lens on the measured deviation? Meaning 2 plus lenses, just to keep it simple. You can bet she billed for it, but probably not as much as would have billed for the case. What about a minus lens? What does that do to the measured deviation? It's like, oh, I think I might know that one. So here's what a plus lens does to the measured deviation. So let's say you have a patient who has XT of 40 prism diopters. Well, now they're not looking through the optical center of the lens. They're looking away from the optical center, but this is a high plus lens. It's a plus 10 diopter lens. And so you've got base in prism of some number. And so that's going to reduce the measured deviation because you got base in prism over an exotropic eye. We can actually calculate how much. It reduces it down to 30 prism diopters. So a high plus lens is going to reduce the measured deviation compared to the true deviation. On the other hand, and that's true whether he's XT or if the patient was ET, you'd still, now patient's ET, but now it's on the opposite side of the optical center. So now it's base out prism for ET. So again, it's going to make it measure less. Whereas for a myopic patient, XT40, they got base out prism they're looking through. So it's building it up. In this case, by 10 diopters, it's going from 40 up to 50 prism diopters. And so that's where we get the minus measures more expression. So technically, we would reduce our surgical dose a bit for the minus 10 patient, and we would increase our surgical dose a bit for the plus 10 patient. But anyway, I've just started doing 5.5 millimeter bilateral medial rectus recessions for all of my ET patients. So, all right. So now it's I lost my it's 20%. It's 2% per diopter of power. So it would be 10 diopters would be 20% increase. So 20% of, or decrease. So 20% of 40 is 8. So it'd really be 32, but yeah. So minus measures more. So this would be 20% of 40 would be 48. Now, minus lenses decrease the cosmetic deviation. This patient actually does have ET if you look carefully, but you can hardly tell. But yeah, and there you go. When you take the glasses off, now you can clearly see the ET, whereas you couldn't before. So it's a little paradoxical because the effective deviation is decreased by plus lenses, increased by minus lenses. Minus measures more. But the cosmetic deviation, it's the opposite, is decreased by minus lenses and increased by plus lenses. I guess I should have made increased green here. But anyway, so even though let's say he's wearing contacts here, even though he looks more ET with contacts, he's going to measure more with the glasses on. The only caveat to that is that his eyes are so small that maybe you won't be able to see the shift as well, but that's not in the books. That's why we use adjustable sutures. So we have a patient who complains, another little bit of a mishap in the cataract surgery. Started off -3 sphere on the right eye and was -3 sphere in the left eye, but somehow ended up with this refraction, +1, +3 times 90. And the patient says, well, you know, it's okay. I can see okay, but I see double whenever I'm reading. And we say, oh, I'm sorry to hear that. So you're seeing double when you're reading. And but the strabismus measurements would show it, but you don't understand, like, was there some injury in cataract surgery? But we want to calculate what's the prismatic power of both of these lenses in the reading position. Could that somehow have something to do with it? So we'll take it one lens at a time. So first, that right -3 sphere lens, that's the easy one. Delta equals h times 3. You're reading 1 centimeter below the optical center. So 1 centimeter times 3 diopters is 3 prism diopters. This is a minus lens, so you use your visual mnemonic to see that that's base down prism. So you got 3 prism diopters, base down prism over the right eye. What about this side? It's a cylindrical lens. So what's the power? All you need is the power in the vertical meridian. You don't really, the horizontal meridian isn't of relevance right now. So to get the power in the vertical meridian, remember way back we talked about how you can real quick get it on the power cross. You put the +1 on the 90 and the +4 on the 180. But we only care about the 90. So +1 and 90. So there's our +1. And so it's 1 centimeter times 1 diopter equals 1 prism diopter. But this is a plus lens, so this is base up prism. So you have base down prism on the right. You have base up prism on the left. And so do those add or subtract? What if you had 3 base down on the right and 3 base down on the left? Well, those would just cancel out. You'd have a net of 0 between eyes. So if you have 3 base down on the right and 1 base up on the left, then it must be 4 base total. It's either, you could call it 4 base down on the right, or you could call it 4 base up on the left. It doesn't matter. It's just the difference between eyes. So you got 4 prism diopters of base, these glasses in the reading position, 1 centimeter below the optical center. It's like you've put a 4 prism diopter base down prism. So does that cause a left or a right hypertropia? I could have added another question here, but I was getting tired. Well, remember, we do our little laser pointer. We follow it through and we say, oh, that's going base down. So that's a right hypotropia or a left hypertropia. So this patient is experiencing a 4 prism diopter left hypertropia in reading position only. The patient is orthophoric in primary gaze. And we had this, like I had a real live patient who this happened to just recently. And he wasn't happy about it. And so I had to do what I'm about to tell you, you do. It was like amazing. It was like something you dream about. Like someday I'm going to find this problem. And then I'm going to prescribe slab off prism and they're going to get better. It'd be amazing if that could ever happen. Well, it did. It happened. So that's what you do. You could try contact lenses, and of course, they won't want to wear contacts. You could lower both the optical centers. That would be another way to compensate. But if you lowered them by 1 centimeter, well, then they're going to have a 4 prism diopter strabismus in primary gaze, so that's no good. So you could lower them by 0.5 centimeter and hope you get away with it, but then you're demanding that they dial in 4 one way and 2 one way, 2 the other. Probably not going to work. And so you could exchange the IOL, since that didn't go so well, or you could give slab off prism. So this is an image of a slab off patient with slab off prism. So it does create a little bit of a line on the glasses, but nothing too terrible. It's always taken off the more minus lens. And really what you do is you measure there. You can measure that deviation in that gaze. So in this case, we probably would have measured a 4, and then you figure out how much they need. And maybe the patient would have been happy with just 2. So maybe you would only have to take 2 slab off, but let's say he needs all 4. And so it's a way of grinding the lens, like they normally grind the lens with this at the center, but then they like shift it in the grinding holder and grind a little bit extra off of the bottom of the more myopic lens. So that's what we would do for him. We would take 4 prism diopters slab off of the -3 lens in order to eliminate the hypertropia in down gaze. So next, we want to talk about the prismatic effects of bifocals. And that includes image jump and image displacement. So image jump occurs right when you're crossing that line from distance to near. You can get some prismatic effect at the edge of the bifocal. Image displacement, on the other hand, is what happens when you're all settled into your reading position and experiencing some effect. So they're quite different. Image jump depends only on the design of the bifocal, whereas image displacement is the combined effect of the lens and the segment. So which bifocal design gives the most image jump? I'm looking over here to see if anybody. Michael Ying Kit Mok, you're on a roll. Which one gives the most image jump? Flat top, round top, progressive, executive? Make it a multiple choice. Round top. Exactly. So here's a new video showing it's. I always think of image jump as dynamic, but you see right there at the edge of this round top bifocal, and I love the example because it's like he's going to cut his thumb off because of image jump. So this is why we're studying this, because we don't want our patients cutting their thumb off because they have image jump, if we can help it. So it's right there at that edge. And the reason that it's bigger in, it's worse in round top is that for round top segment, the optical center is way down here. So you're way away from the optical center. Whereas a flat top segment, you're quite close to the optical center. So there's some minimal jump. An executive segment where they split them across, there's no image jump there, and there's no image jump for the progressives. Notice this has nothing to do with whether there's a hyperopic, whether it's plus or minus lens under it. It's just round top, going to give you more image jump. Now that's different than image displacement. So to understand image displacement, first think about it. The flat top segment in the reading position is going to be like a base up prism. The round top in the reading position is going to be like a base down prism. So then you combine that, you combine the lens with the bifocal. So for example, this is a plus lens. Oh, we'll go to this one first. So a plus lens, when you're down here in reading position, it's like you already got some base up prism. And then you add the bifocal onto that. Now you got more base up prisms. You're going to get a lot of image displacement down here. Whereas if you put a round top on a plus lens, they cancel out. So you get minimal image displacement. In contrast, for the myope, you put a round top on a myope, and you're going to get a lot of image displacement because it's base down, base down. You put a flat top, they cancel out. So for myopes, it's easy. Flat top gives less image displacement and less image jump. But for the hyperope, the flat top gives less image jump, but the round top gives less image displacement. So which one is better? Well, although you saw that that person was just about to cut their thumb off because of image jump, we've been teaching that image displacement is probably more important. And so technically, according to what I've read, round tops may be best for hyperopic patients. But in real life, round top bifocals are more expensive, they're harder to get, they're harder to fit. And so pretty much most people just get flat tops anyway. So, but even though most people get flat tops anyway, again, that's the 90%, the 95%, but maybe you got a patient who's like got new bifocals, but they're hyperopes and they're flat tops, and they really they feel like they're confused when they're using them. Well, maybe you can switch them to round top bifocals and make their life a little better. Because you were here, because you heard that one little snippet. Fresnel prism, also known as press-on prisms. Professor Fresnel had a nice idea, which is instead of just having one big slab, if you put a whole bunch of little prisms next to each other, then you can get a whole big amount of prism power in a flat thing. And you can get lenses that way too. A lot of lighthouses have big Fresnel lenses. So you can get up to 40 prism diopters, and they're convenient for us to use. They're lightweight compared to big heavy prisms. They're really hard to clean, and they do reduce visual acuity, especially with higher power. I have an example. So this is a lower power Fresnel prism. So you see I took the picture through half of it, so there's some displacement here, but you can tell which one is through the prism. It's just not as clean an image. And I think I can't remember. I think that was only like a 4 or a 6 or something. And then here comes the 20, or maybe this was the 30 prism diopter. You got like a lot of blur. You got chromatic effects. It's just ugly. So really, when someone's wearing like a 40 prism diopter Fresnel prism, they're wearing a patch. So this is, I think this is this was like an 8 or a 10, I think, Fresnel that we have stuck onto the glasses just so you can see what it looks like. But one time, I don't want to get into politics or anything, but Hillary Clinton had fallen and I think she had a 6 nerve palsy because she was caught in public with this Fresnel prism on her left eye in 2013. Those were the days when we all liked each other. Chromatic effects of prisms. So you may have noticed in the very first picture of prisms that it's not just that the light is bent, it's turned into a rainbow, just like we used to study in elementary school science class. And that is because the refractive index varies for the same material is different for different wavelengths. So it's a higher refractive index for high energy blue light. So blue is bent the most. Well, in ultraviolet, violet and ultraviolet, you know, they're at the high energy side of things. So they come barging into the prism, and so they get like bent out of the way much more, whereas the red is the lower energy, longer wavelength, kind of chilling on its way through. It's moving slow, so it's moving. It doesn't slow down as much. It's just easy, so it doesn't bend as much. So blue is bent more, red goes through straighter. Probably way more words than I needed for that. So this also is an effect in lenses. So in lenses, blue light is going to be refracted more intensely than red light. So the blue rays will come to focus closer to the lens than the red rays. And this happens inside of the eye as well. In fact, the eye has a good amount of chromatic aberration. I'll show you another slide in a minute. But first, I'm just throwing this one at you. What is the Abbey value? Well, you're thinking it must have something to do with, no, you can't take a reciprocal this time. It has something to do with chromatic aberration, because why would I have thrown it in just then? Yes, I was looking last night to find an image of chromatic of image displacement, and I couldn't. So I'm going to have to make my own. But I didn't have the materials I needed to do that. If I'd started on it last week, like I planned to, I would have had that. But. So yes, the Abbey value has to do with chromatic. It's a measure of the chromatic aberration or dispersion of the lens. So a higher value is a better quality lens. So human eye has an Abbey value of about 45. So if your spectacle lens can hit 45 or higher, then you're not going to notice any aberration. Crown glass is like 60, so it's awesome. But polycarbonate lenses are terrible. They have an Abbey value of 30. And the higher index lenses tend to also have lower Abbey values. But, you know, some people insist on giving polycarbonate lenses to all kids because they're bulletproof. But I mean, just the ordinary plastic is also quite resistant to breakage, and polycarbonate lenses scratch a lot. I think it's excessive. And then you're giving them, you're subjecting kids to chromatic aberration they don't need to necessarily have. So anyway, this isn't just a idle distraction. This may be something you could possibly be asked about. So here's the chromatic aberration modeled in the human eye. And so you see it's pretty strong chromatic aberration. Our retinas and our brains are calibrated to somehow deal with that and manage it. And it's the basis, though, of the duochrome test, also called the bichrome test, where we use red and green filters to create a spherical difference, not of 3 diopters, but just of a half diopter. And the idea is that then you can refine refraction without having to worry that accommodation is throwing you off. So it looks something like this. You've probably seen it before. It's black letters on red and green backgrounds. We adjust the sphere. Well, you start by over-plussing the eye. So you give too much plus, and so too much plus is going to push that red line into focus on the eye and get the green line way out of focus by a half a diopter anyway. So you give too much plus because you want to relax accommodation. Because if you start at the minus side, people could accommodate their way back into, you could still get fooled by accommodation if you don't start with over plussing. So you over plus, and then you ask which side is clearer, and they're going to tell you the red side. And so then you give a little more minus. And that's easy to remember because they said the red side's clear, so you give red minus. until they say that they're equal on both sides. And then when they're equal on both sides, then yellow's in perfect focus, and that's the optimal for viewing in white light. I think I'm getting dizzy from this slide. Getting a little, and I have a nice after image now. So that is other optics of note: magnification, low vision, mirrors, prisms. And now, before we move into our final round, what was that formula for Prentice's rule again? Remember, this is an important one, so I just want to make sure you. Oh, what about focal length? What was that formula? So Prentice's rule, that was delta equals h times d, right? So focal length, oh, that was the easy one. That's like 1 over d. How about the Vergence formula? I completely forgot. Well, it's u plus p equals v. Oh, I didn't fix this one. U plus d equals v, but work in progress. So delta equals h times d, u plus d equals v. Focal length is 1 over the diopters. We're just reminding you of these formulas. Spherical equivalent, we'll throw that one in, sphere plus half cylinder. Oh, another question already. How about the refracting power of a spherical surface? Oh, now we're getting a little bit more complicated. It's more than one letter. How about the reflecting power of a spherical mirror? How about the SRK formula? Just seeing if you were awake. So refracting power of a spherical surface, n prime minus n over r. You determine whether it's minus or positive power by drawing a box around the surface and coloring in the higher refractive index side. A power of a lens immersed in fluid, you use that same formula, but you divide it by itself with the air on the top and the aqueous on the bottom, or vice versa. So it's really the difference, it's the ratio of the difference in refractive index. And then the reflecting power of a mirror is 2 over r. Remember, that's just taking n prime minus n over r and putting a 1 and a negative 1 here. So these are all three the same formula. And then the SRK is A minus 2.5 times the axial length minus 0.9 times the K. I think even in the world of AI, IOL calculations, we still want to know that. Oh, more questions. And how do I calculate axial magnification? Axial. That's not transverse. Oh, that's just the square of transverse magnification. What is the power of a simple magnifier? Well, there's the simple answer, d over 4, or d times the reference distance, d times 0.25 meters. Power of a Galilean telescope? It was so long ago. How are we supposed to remember that long ago? It's power of the eyepiece over the power of the objective. How about an astronomical telescope? I'm not telling you that one. Okay, it's the same. Power of the eyepiece over power of the objective. A spectacle lens is 2% per diopter power. And transverse magnification is image distance over object distance, which is, you can also, which you can determine by the reciprocal. It's 1 over u over, 1 over v over 1 over u. Sometimes in some books, a lot of books, u, the big U, is Vergence, but the reciprocal of u is like a cursive u and a cursive v. But I could never follow that when I was trying to learn this stuff. So finally, in our last time, the last of our time together, optics in the office. So we'll talk about, we've already reviewed our formulas. we'll talk about prescribing glasses, instruments, and presenting symptoms. So we may run a little over 6 hours this time because I've been digressing so much, but it's okay because it's all recorded. So you can always come back and have it help you put you to sleep at night. It's better than Calm, the app. So we'll talk about retinoscopy, high index lenses, what to do when a child won't wear glasses. Oh, I don't know if I'm talking about that. Anyway, we'll talk about some of these. Oh, but first, another question. How do I refract a patient with a difficult retinoscopic reflex? Yes, you can try to put them in the autorefractor, but autorefractors are not that good when the retinoscopic reflex is ugly. You can simply move closer. That actually works pretty well a lot of the time. The only thing is that, like, if you're 10 centimeters away, then your working distance is 10 diopters. But if you're like off by 1 centimeter, then it's like 9 diopters versus 11. So, but you can at least like find cylinder from that distance and then you back up. And so that's what I do. Concentrate on the center of the reflex. Remember, we talked about that with spherical aberration. Consider a contact lens over refraction for patients with irregular astigmatism. Try the autorefractor. Sometimes just do a subjective refraction. And we're not going to go into the stenopeic slit, but there is a way to refract using this slit that I have never ever used. But it involves refining the sphere one way, then rotating it 90 degrees, refining the sphere another way. So it still is rather subjective. You could prescribe pinhole glasses, but I understand they reduce the amount of light coming into the eye. What are high index lenses? They are plastic lenses, 1.66 and up. We already alluded to them and their Abbey values. Glass lenses up to 1.8. I remember hearing about people who would like go to Germany to get their 1.8 index glass lenses, which you couldn't get in the US because they don't meet safety standards, but you can understand why if they're so optically pure and thin. Speaking of thick glasses, how can the appearance of high minus lenses be improved? This is an old classic. So I'll give you a minute to imagine that, again, that I'm the oral examiner. Dr. Monsalve, how can the appearance of high index, high minus lenses be improved? Oops, I just gave you a hint. So the hint was high index, use high index lenses. Because with high index, actually, you could do a cycloplegic refraction because maybe he's over minus, probably not by 20 diopters, but you know, things happen. Smaller frames, because the curvature is gonna, if you have a lot of curve, then the bigger the frames, they're gonna quickly get thicker as you get off to the edges. Use a high refractive index material. So remember, D equals N prime minus N over R. So if N prime minus N, if you can double that, then you're going to cut R way down. So the radius of curvature is going to be much, much less. And so the lens is going to be flatter. And if it's flatter, then it's not going to be as thick at the edges. So the higher refractive index material you can get away with, the thinner the glasses will look for the same power. And then the smaller frames too, do those two things together, and you can end up pretty well, even with those high refractions like you see there. Frames that hide the thick edges, you know, another thing you can try. Of course, we can consider contact lenses. Sometimes the lenses can be beveled too on the edges. Another question. Are you getting to like the grit-faced emoji for questions? Is that like resonating? Who will have more trouble adjusting to new contact lenses? Pre-presbyopic myope or pre-presbyopic hyperope? Well, you could just memorize this. It takes a long time to work out the specifics. Good answers. Index, change lens material, small glasses. The myope. You're right. It is, now why is it the myope? So I can help to explain it, but you can do the math. And if you figure out the vergence at each step of the way from the object to the front of the glasses, to the back of the glasses, to the front of the eye versus from the object to the contact lens, it all works out that it's truly a lower accommodative demand. But we're not going to work out the math. You'll just have to trust me on that. But the other is that there are prismatic effects where minus, and this is easier to remember because minus lenses act like base-end prism when you're reading, right? So here's your minus lenses, you're reading, you got to converge. Oh, look, you've got help. You've got base-end prism when you converge through the glasses. And so if you now switch to contacts, you're no longer going to have that base-end prism. So it's going to be harder to converge. But it's also hard, but there are also definitely, and more importantly, increased accommodative demands. But this just helps you to remember that it's the myope. And then again, the hyperope, you know, that might save them from having to switch to reading glasses if they can go from glasses into contact lenses, because their accommodative demands are going to be less, and they're not fighting against their prismatic effects. 27-year-old patient returns to you a week after you performed a careful, presumably accurate, refraction. He's complaining of continued trouble with distance vision, especially at night. So what are 4 causes of night myopia? Now, it could be the patient has retinitis pigmentosa, and often you think it when they first say it because they tell you they're night blind. But they don't really mean they're night blind. It's not like they lose their way in the movie theater on their way to the seat. They're just having trouble with their night vision. So there's 4 things. I'm giving you a minute to think it through. 4 things. What happens at night? See if I could, maybe I should make this more interactive so I could call on people. Nah, that'd be mean. Pupil dilation. The pupils get big at night. When the pupils get big, you expose the periphery of the lens. The lens has positive chromatic aberration. It's stronger in the periphery than it is in the center. And so you become more myopic. The length of the refraction lane range. Oh yeah, we got it. Somebody got, Bilal Abdullah got positive spherical aberration. We'll get to Purkinje shift. That's the fancy one. Length of the refraction lane. The refraction lane is at best 20 feet. When we're driving, something is close when it's 20 feet away. And it's not a lot, but it's a little. 1 over, you know, it's a 6 meter refraction lane, 1/6 diopters of extra minus that you really should or could add on to any refraction that's subjectively refined in an eye lane to properly correct a person for infinity. 1/6 of a diopter. It's not quite 1/4 of a diopter, but you know, most people, if people have a tiny bit of accommodation, they'll be okay. Here's the Purkinje shift. Lower light levels at night cause us to become more sensitive into the blue end of the spectrum, And remember, blue light is refracted more strongly by the eye. And so you get myopic shift that way. And then this one's a little weak, but no accommodative targets in the dark. So you kind of lose it's like you lose your accommodative mojo and you just like dial it in too much. You focus on the headlights and just start like over accommodating and make yourself myopic. I don't know. That's sort of a hand waving one to me, I'm guessing, but just trying to come up with one. So the solution then for each of these first three is to just put a little bit more minus power in the glasses for driving. But if you have a pre-presbyopic patient, that could throw them over into becoming a presbyopic patient. And so I once had a patient who just really wanted to get it fixed, but who happened to have an accommodative insufficiency. And so we had to give her separate driving glasses for night driving. Question, name one disadvantage of a progressive addition lens. Well, I've got one here. I'll tell you that it's not very clear. Like when I do that, it's kind of distorted, kind of moves all around when I do move my head around. So they have marked irregular peripheral astigmatism, especially in the highest powers. So see, I put this in front of an Amsler grid. I think I did this one. Maybe Guy did it. No, I would have had his name on the bottom of the slide. So you see, it's, yes, you get your ad, but you get this, a lot of distortion. Like that can be very annoying for some people. And it depends on the manufacturer. So there's compromises between trying to push that clear area out. And so Hoya here shows the traditional design where it's a very narrow channel. There's bad music, very music. And then design. What they don't tell you, again, narrow channel, can't even tell what's on the record. Wide channel. What they don't tell you though is there's still a compromise here in that when you have the wider channel, you have even more distortion when you're outside the channel. So it's not perfect. Oh, another right on question here. How does one deal with a patient who is not accepting spectacle correction of astigmatism? I don't know if you've ever had that happen, but you change the astigmatic correction of patient's lens. They say they can see better, but they don't like their glasses. They say that they feel like they're in a fishbowl. Everything is coming up at them. They can be very unhappy. I had one attending in residency who talked about the limp wrist with the glass, the limp wrist syndrome. These are no good. So she said, just never change the astigmatism in patients' glasses. But I've gotten past that, and I'm brave, and I changed the astigmatism with aplomb. I think that's the right word. And I've mostly gotten away with it because they can see better. So anyway, here's the main problem is if you have oblique astigmatism and you correct it, you create some distortion of the image, as was shown even in this. That's why I chose this picture. So now this door frame, it doesn't look like it's rectangular anymore. It's more like rhomboidal. And that's annoying somewhat. But what's really annoying is that the right and left retinas, they're no longer corresponding on the same place on the retina. So there's a disparity. So the right eye sees one thing and the left eye sees another. And since they don't line up, it begins to create a 3D image. So depends on where your monitor is and how well you can cross your eyes and fuse stereograms. I can't, this worked in, it works in our auditorium, but I can't make this one go right now. But if you could fuse this stereogram, you'd see that the door looks like it's falling towards you. And so that's what they say. I see like things are coming, the floor is coming up at me. It's less about the shape of things and more about the depth that they don't like. So to fix it, if you rotate you'll lose, the vision will be lost. I mean, you don't get as sharp a vision, but you rotate the axis of astigmatism to be more vertical is the best way. But you can also cut down on the cylinder power overall. There are a couple of ways that don't reduce vision. One is just reassuring patients that eventually you'll get used to it. Another is the shorter the vertex distance, the less of an issue this is. So if they happen to, for some reason, choose like big, fly eye glasses, you could try to get them out of those. This has to do with how the lenses are made. So, if you've got a good relationship with the optician and the optician is for some reason grinding plus cylinder on the front of the lens. I don't know, I should have you take this out. They're all minus cylinder lenses now. They're all lenses have cylinder ground into the back as minus cylinder. Doesn't matter how you prescribe it, they're going to grind it out of the back as minus. Compromise on acuity, as we said, rotate the cylinder towards 90 or 180 or decrease the power of the cylinder. Again, contact lenses, but try going into your oral exam and just each problem say, oh, well, I would prescribe contact lenses. Oh, I prescribe contact lenses. So, you need to know the other answers too. Why are there different Jackson cross cylinders? So here you see that the one in the clinic here is a plus or minus 0.25. And so that is optimized for being able to tell a difference at around the 20-30 range. However, if your retinoscopy has only gotten you to 20/100, say, and you say which is better, 1 or 2, well, they're going to say they look the same. So your refraction is going to go real quick. Which is better, 1 or 2? Or the same? They're the same. Okay, good. Now we'll switch to power. Which is better, 1 or 2? Well, they're the same. Okay, good. They're the same. Now we're done, except the only reason you're done is because they're not at 20/30 vision, they're at 20/60. So you need to, in these cases, you can pull out the handheld Jackson cross cylinders because they have different powers, and then you manually do the flip. I've done that twice in my career and made a difference. Again, it's like, oh, I think this is one where I need the handheld Jackson cross cylinder. Where is it? 20 minutes later, it's like, okay, we've got it. So, whoops. So that's why they're different powers. And note that the prescription for this Jackson cross is minus 0.25, and then it takes us a half to get to there. So plus a half, and then the axis is just wherever you're holding it, axis, whatever. Spherical equivalent is plano, right? Sphere plus half the cylinder is plano. So you know it's a Jackson cross cylinder if it's plano spherical equivalent. And the cylinder has to be, double the sphere. Okay, we're into ophthalmic instruments and presenting symptoms, optics in the office. So, or no, that's part of, we're down to these last two things. So we already talked about OCT. I snuck that in early. We'll talk about trial lenses. That's what this is. Lens clock, lens meter, retinoscope, keratometry, slit lamp, applanation, fundus lenses, and lasers. So For trial frames, it is possible to use them incorrectly. The lenses are designed for these numbers to be facing forward. That reduces the aberrations that the patient will see. And you want them in the back slot so that they have the proper vertex distance. So the numbers go in the back lens, the numbers go in the back. And then the sphere goes in the back. Sorry, I was reading the chat there. And then you put the cylinder in the front. And you can, then you smaller lenses go in front of that. And again, the numbers need to face forward. So you can do walk around trials with trial lenses in the office, but they're still not a perfect substitute because they don't have the same base curve. They don't have the same aperture. So even if a patient thinks that they're okay with the lenses and trial frames in the office, they still might not like them when they actually get the glasses. What fundamental principle underlines the lens meter? Lensometer is the brand name. Lens meter is the generic term for the thing that measures your spectacles, measures spectacle lenses. I'm not sure if this still comes up, but I think it's good to know. It's the optometer principle. That is for the lens meter, not for these. These use image displacement, generally speaking, to look for the power, but the optometer principle. So what is the optometer principle? So there is a telescope in there too. So I'll get to the telescope part, but the optometer principle is the key here. So what happens is if you were to just try to measure a lens by moving a target back and forth, you wouldn't have a linear. It would be just very hard to like if it was a minus lens, how are you going to focus that? You'd have to anyway. But the optometer principle, you have this strong lens. It's called the standard lens. And then you put the target at one focal point of the lens and you put the unknown lens at the other focal point of this standard lens. And when you do that, if the target is at the focal point, then you're going to have parallel rays of light coming into the viewer's eye. And so the target will be in focus. But now you put an unknown lens at the other focal length. We don't know what the power is of this lens, but it's now going to cause these rays of light to converge. So now the target's going to be out of focus. So you now turn a knob to move the target, in this case, closer to the standard lens to diverge the light until you have parallel rays coming out. And the beauty of this is it's a linear scale and it goes for works for plus and minus lenses. So that's the optometer principle. And so in a lens meter, you have this standard lens, that's the optometer, whoops. You've got the target, it's illuminated, 0 is at the focal point of the standard lens. This platform where you put the spectacle is at the other focal point of the standard lens. And here's the telescope, the Keplerian telescope. And it doesn't matter what your refractive area is, because that's why you have this telescope here. The telescope you focus to control for your own refractive error, presbyopia, whatever, so that when this is set at 0, everything should be in perfect focus, with no lens. So when this is set, when the target's at 0 and there's no lens in the unknown place, you can focus the eyepiece so that for yourself, so everything is in focus. And the telescope also enhances your detection of parallel rays, enhances your detection of focus when the lens is neutralized. So here's what the American cross target looks like. There are other targets used around the world, but the sphere line, the cylinder line. And so, and by the way, we are generally measure what's called the back vertex power. That is, the temple should be away from you. However, when measuring bifocals, segmented bifocals, you're supposed to turn it around and measure the front vertex power by convention. Just a fun fact. So you don't yell at the optician that they made the bifocals wrong. Here's what you see. Here's an image using my phone that I took of the view through the lens meter. And so there should be no displacement of this center, but if there is displacement, in example, this one's displaced down, that's because there's base down prism. And you see there's a number there. It's the number 3. So this is 3 prism diopters of base down prism in this eye. If you want to measure prism, but it goes all the way off the chart, it's say more than 5 or 6, or if you just forget which way this is supposed to go, you can put in neutralizing prism. You can put it here. This is base out prism neutralizing. You can also, if you have this style of lens meter with the slot, you can stick a little tri-lens in there. Or we have the fancy ones that have a knob where you can dial in the prism power. So I made a little video first showing, this is the way I do it anyway. Before I even use the lens meter, I put this knob at 0. So I know it's going to be in focus. Everything's going to be in focus. And then I'm going to adjust the eyepiece. So we set this at 0. And then there's no lens in there, no unknown. I set the prism. Here's our adjustable prism thing. Put that at 0. Now I look in here and it's going to be out of focus, but it should be in focus. So we're going to turn the little knobby until that target's in focus. Now we put our unknown lenses. We turn in the knob until it comes into focus. You see this lens has power. So when we get away from the optical center, it moves around. There's adding prism and removing prism. So you see that was about 2 prism diopter prism. So that is sort of the basics of using a lens meter and what's inside of it. When we're measuring prism power, we need to know the effective prism power that the patient is experiencing, because you don't know for sure that the optical centers are where they're supposed to be. So there could be more prism than you think, or less. So what I do is just put a mark over each pupil. Like in this case, I'm closing my left eye. I might even cover his left eye so that I'm sure he's looking with his right eye. But anyway, you put a dot over each pupil, and then you put the dot in the middle of the lens meter and measure the effective prism there. The retinoscope. So the retinoscope, they have different, there's a bulb and a lens, and the idea is you want diverging light going into the patient's eye. You do not want to be focusing the light. That's for something special. So here the sleeve's in the wrong place. So we're going to slide it down. That's better, because now there's no place that we can focus the light. So that's converging light with sleeve up. That's diverging light with sleeve. Here comes the sleeve's going to go down. There. Now, no matter where I put it, it's diverging light. So we throw diverging light into the eye and then look at what comes back to do our retinoscopy. At neutralization, as soon as the intercept gets any light into the pupil, the entire pupil fills with light. And that's because, and I'm not showing the source, but there's light coming in, but it means that the far point of the eye is matching the peephole of the retinoscope. So since the far point of the eye matches the peephole of the retinoscope, then all the light coming from the eye gets through the peephole and goes into your eye, the examiner's eye. This is, there's a retinoscopic simulator available. I made this video based on an earlier version, so the newer one's a little fancier. I have the link there. Just type retinoscopy simulator, but it's kind of fun to play with, to look at the with and against motion, etc. Image doubling, that's something that we use in ophthalmic instruments. In an image doubling, you take a variable prism, and if you're 100, so if we're 100 centimeters away and we can see both the object and its virtual image at the same time, there's a way to do that. then we know that they're separated by, in this case, 100 centimeters, 10 prism diopters, so they're separated by 10 centimeters. What if we wanted to know exactly how tall these glasses were? Well, we would reduce the prism until the top of the object was touching the bottom of the image. And that's what's happening here. So in this case, it was 5 prism diopters that was needed for the, and so we know then that these glasses are 5 centimeters tall. And the beauty of this is that even if the glasses are, if somebody's wearing the glasses and they're jumping up and down on the trampoline, the object and the image both move at the same time, so you can still adjust your separation even though they're moving images. And so when we're trying to look at the eye under a microscope, under the slit lamp, we can use this optical doubling to measure things, as you'll see in a minute. So this is just demonstrating in our office. You see how you can see the object and the image at the same time. And so we can use that. And when the one's touching the other, that's the proper separation. So now we can figure out mathematically it's 2 prism diopters and say that's 3 meters away. Then we know exactly how tall that box, that little square is on the wall. So that's using optical doubling to measure the size of an object at a distance. What fundamental principle underlies keratometers? Optical keratometers. I'll just pause again. While you're thinking of that, we have an exciting moment, which is that this person is currently watching the video. Luke 2761125. Those aren't his glasses. He doesn't wear glasses. Optical keratometers. The fundamental principle is I'm blanking on it, is using the reflecting, it uses the reflecting power of the cornea to measure corneal curvature and therefore corneal power. So it's also using optical doubling in some cases and vernier acuity as well. So this is the Javel-Schiatz ophthalmometer, which measures corneal power, and it projects these 2 images onto the cornea. This little space invader halves onto the cornea, and then the cornea reflects those images. And the stronger the cornea, the more curved the cornea, the smaller the reflected image is going to be, because it's a more and more powerful convex mirror. So also, when they're not aligned with the principal meridian of astigmatism, then you'll see that they won't then line up as you look at the reflection on the cornea. So when it's not aligned, you've got to rotate this arm rotates. And so you rotate the arm until they are lined up with each other. And now this is the correct separation. But let's say you have a stronger cornea, a steeper cornea, that's going to make for smaller Meyers. So now we're aligned, but they're not aligned. So you got to turn the knob. It separates those boxes until the images get closer together. And so once they're exactly the right distance, then you can read off the power. Let's say you have a relatively flat cornea. That's not as strong a reflecting power, so it's going to make bigger Meyers. And so then you turn the knob and you increase the separation until they're just touching. So see, you're using your vernier acuity both here and here to measure this, the size of these images. So with this style, you have to do both a vertical, you have to do 2 meridians separately, 1 and 2 vertical and horizontal. In this case, that's an old picture of Mike Repka. So you get then from that the exact radius of curvature of the eye, because it's measuring the eye as a mirror. And then on the other side of the scale is the diopters. But this is inferred assuming that the cornea has a particular refractive index. In fact, it's assuming that the refractive index of the cornea is 1.3375, because then a 7.5 millimeter radius of curvature gives you a corneal power of 45 diopters. So, so that's one form of keratometry, but again, it's using the cornea as a mirror, a convex mirror, to measure corneal curvature, and therefore inferring corneal power. And the Bausch and Lomb keratometer, it does the same thing, but it does both meridians at one time. And so this one does use a doubling prism to, and then you turn the knobs to get things to line up, but we won't go into the specifics of that. Well, what fundamental principle underlies the slit lamp? These pauses are to wake up those of you who are still alive. Funny how silence can get your attention versus the endless babble of my voice, like a babbling brook trickling down the lane, down through the meadow, putting you all to sleep. The fundamental principle is the common pivot point. So good old Goldstrand, after he got his Nobel Prize for figuring out the optics of the eye, also figured out this, that if you had both an illumination and a magnification system on a common pivot point that could move back and forth together, then you could always be in focus where the light was in focus on the eye, and therefore get a good picture of the images of the structure of the eye itself. Plus, the narrow beam doesn't hurt either to get an optical cross-section of the eye. So no matter what slit lamp you see, you're always going to find a common pivot point of the illumination and the magnification system, whether it's the Zeiss style or the Hogstrite. There's the common pivot point there. That's all you'll always see that. Also, in terms of magnification change, there are two ways to change magnification on the slit lamp. One is that these eyepieces do change out. So if you ever feel like your slit lamp is just like too powerful, it could be that someone put in higher power eyepieces, and you might be able to find lower ones sitting around somewhere. And then the other thing is to change the objective. So on the other side, you know, there's this knob that changes the magnification. Have you ever looked on the other side of the slit lamp to see what happens when you turn the knob? So it's actually flipping higher power objectives into the into and out of the view when you flip that. I tried to get this to think exactly. I'll try again. Ready? Almost. So next up is applanation. And so when we're doing corneal applanation, we're using this split field plastic prism. So once again, we're using optical doubling to help us measure something, because, well, let me explain what we're doing. And I'm also going to explain what that little red line is for on the applanation tip holder. Not that anybody's allowed to use these anymore. Infection control has a heart attack when time we touch an eye. Anyway, so when we push this against the idea is we want to push against the cornea until we flattened exactly 3.06 millimeter diameter of cornea. And that's because when you flatten 3.06 millimeter diameter of cornea, then the pressure against the eye in dynes is equal to the pressure inside the eye in millimeters of mercury. So 3.06 is the endpoint. So how do you know that's 3.06 millimeters? Well, that looks a little too big. So maybe we'll back up a little. Oh, no, that's definitely too small. So maybe we'll go up. And I think that's about right. But then if the cornea moves a little, say you've got a little ruler inside there, you know, how are you going to, the eye moves a little, you just can't tell. You can't be sure that it's 3.06 millimeters. So that split field plastic prism actually shifts the top image over by, guess what, 3.06 millimeters. So it's using optical doubling, in a sense, to separate it by that much. So now there's no question you've got too much force because it's these are way apart. So then you back off and you come down too far and now there's not enough force. And then, oh, right there, it's just right. That's separated by 3.06 millimeters. And look at that, you're using your vernier acuity to give the most precise measurement possible of that endpoint. So that's how and why, the how and why of the applanation tonometer. And now the red line comes into place because of not every patient has a perfectly spherical cornea. And so, so the question is, name 2 ways to compensate for high corneal astigmatism when performing applanation tonometry. I just gave you a hint. And Bilal already got it. Red line for high astigmatic patients, that's one. But there's another way. It's easier. It's way easier than the red line. Average between the 2 measurements at 90 and 180, exactly. So if significant astigmatism is present, the applanated area will be elliptical. So it's hard to determine when you're at 3.06 millimeters because now you've got an ellipse. And so if you rotate to align with the red line, it turns out that that red line, the minus cylinder, then that puts the ellipse at just the right place to where you have the equivalent of the 3.06 millimeter diameter. So you take the axis of minus cylinder. So in this case, if the axis of minus cylinder was 135, I think, then 20, 30, 40, 50, 60, 70, 80, yeah, so 20, 30, 40 was 138, then you would applanate just like this. But if the axis of minus cylinder was 180, you'd need to rotate that up and put it there. So, but because here's the problem. If you have, say, a flat cornea horizontally, then when you look at this, you're going to say, oh, that's too much pressure against the eye. So you're going to back off, even though this is the right amount. So then you're going to get an artificially low reading. And yet, same cornea, if you rotate it 90 degrees, now you say, oh, I need to put more pressure against. You're going to dial it up and get an artificially high reading. But if you put the axis of minus cylinder exactly on that red line, now you're in the major axis of the ellipse, and that's going to give you or you're oblique to the major axis of the ellipse. So that's going to give you the proper applanation. But again, just easier is take this pressure, and average the 2. Why does the diameter of the applanated surface need to be exactly 3.06 millimeters? This is another one just to see if you're awake, because I just told you. Like I just told you. I'm so mean. It's because at 3.06 millimeters, the pressure against the eye in dynes, this is 1 dyne, 2 dynes, times 10 equals the intraocular pressure in millimeters of mercury. So that's not, they didn't just leave off the 0. That is dyne. So it's this number times 10. So that's why that's 14 millimeters of mercury. Question. There's Luke 2761125 again. Why can't we see the retina directly with the slit lamp? It's like you can see the cornea, you can see the iris, the lens, the vitreous. What happens? Why can't we just push it all the way up against the eye and see the retina? Why have to use all those lenses? Well, I'll tell you why. You've got this 60 diopter lens in between you and what you're trying to see. And the closer you get, that lens is converging the light rays into, and the farthest back you can get, no matter how close you get, is into the anterior vitreous. So what you need is a way to put diverging light into the eye. And that can be either with the ruby lens, a little minus lens to diverge the light on the way in, or here it is again. Nobody really uses these anymore, but because the other lenses are so much easier to use, but we used to use these. So it diverges the light, then you can get all the way back to the fundus. Or gold mount contact lens, same thing. It's basically replacing the curvature of the front of the cornea with a flat surface. Or the 90 diopter lens, completely different mechanism. What this is, it's indirect ophthalmoscopy. It's taking the image, it's reconverging it into an aerial image in front of or on your side of the lens, and then diverging it again. So that's why when you're in focus on the eye and you put the 90 or 78 diopter lens in place, that's why you got to back the slit lamp way up, because you're trying to find this aerial image and get it into focus. So the indirect ophthalmoscope uses that same concept. It uses a condensing lens to capture these peripheral images and bring them back into the eye of the observer. And they used to just be a monocular indirect ophthalmoscope. You might be able to see them around somewhere in museums mostly, because the binocular indirect ophthalmoscope is so much more effective. But for the direct ophthalmoscope, you're losing all the peripheral images and only getting about a 7 rays and only getting about a 7-degree view, whereas for the indirect ophthalmoscope, you get about a 25-degree view, capturing more of the peripheral rays. And so the idea here is the headpiece of the binocular indirect ophthalmoscope is bringing your pupils closer together and the light source close together as well, so that you can get the light into the pupil and get both of your pupils in, so that both of them can see through the pupil and the light gets in so that you can see in there. So that's sort of the basic concept of an indirect ophthalmoscope. Now, you may have noticed the small pupil setting on indirect ophthalmoscopes. And so have you ever noticed what happens when you switch to small pupil? I have a video here of that. So here's normal pupil, small pupil. So you see what happens? It's moving your pupils even closer together, and it's bringing the light source in more tightly as well, so that all of that stuff can fit through a smaller pupil. So what do you think the downside of that is? Well, for one thing, your perception of depth is going to be that much worse, because it's, your pupillar distance is almost, down to almost nothing. And you're going to get more glare because the light source is so close to the pupils. In fact, I find that in my experience, the 28 diopter lens, it's always a terrible view when the scope's on small pupils. So you want it on big pupil whenever you can. But when you have to, you can put it on small pupil. So with it in the normal position, it takes your 60 millimeter pupillary distance and it cuts it down to 15 millimeters. So your stereopsis would be reduced. Your perception of stereopsis would be impaired by about 4-fold, and small pupil would be even worse. But then there's axial magnification. So it gets complicated when you start thinking about the magnification, because there's axial magnification. So the transverse magnification, when you do indirect ophthalmoscopy, it's just the ratio of the focal lengths of the eye and the lens. So it's the power of the eye over the power of the lens. And so, for example, in the eye, we know is about 60 diopters. So so which lens gives the least magnification, distortion in indirect ophthalmoscopy? And I'll give you multiple choice. It's either the 30, the 20, or the 15. Which one gives the least magnification distortion? So we're going to work our way through and figure it out. So transverse magnification of a 20 diopter lens, it's power of the eye over power of the lens. So that's 60 over 20 is 3x. So the transverse magnification is 3 times. So when you do indirect ophthalmoscopy, that image of the, if you see a little nevus in there, it's going to look 3 times wider across than it would in real life. But the axial magnification is the square of the transverse magnification. So it's going to be 9 times higher. So it's going to look 9 times taller. So that sounds like a lot of distortion. But then remember that the eyepiece reduced your perception of depth by 4-fold. So that's 9 divided by 4 is 2.25. So actually this nevus that you're looking at, it's 3 times wider, but it's only 2.25 times higher. So there's been reduction of what it would look like if you could just like shrink yourself down and get inside the eye and look at it. A 30 diopter lens, that's 60 over 30 is 2x, 2 squared, axial mag is 4x, but the eyepiece, after reduction for the eyepiece, it's down to 1x. So that gets even more flattening. Whereas a 15 diopter lens, the transverse magnification is 60 over 15 is 4x. The axial magnification is 4 squared or 16x, but then you reduce it by 4 back to 4x. So with the 15 diopter lens, there's no relative flattening of the image. So that is your answer, as Natalie and others noted. It's the 15. Now, does that mean that if we're looking at tumors, we should always use the 15 diopter lens? No, just know that if you always use the 20 and for some reason you pull out the 15, that you're going to have a different perception of the depth of things. Same goes, probably more realistic, because you don't see 15s around that much, at least I don't, is switching from a 28 or a 30 to a 20. You're going to go from 1 to 2 flattening with the 30 to 2.25 to 3 flattening. So more flattening with the 30. All right, we're in the home stretch here. We have lasers and then we have just symptoms. So name at least one fundamental property of laser light. And there's 4 to choose from. One fundamental property. Just 1 out of 4. We already used one word a lot today. It was early in the morning, though. Monochromatic, we'll take it. Coherent, polarized, and directional. So we know all 3 of those. Directional means it's non-spreading, so you can bounce a laser off the moon and back. and it just doesn't spread. And in my 2010 lecture, I have a very exciting rendition of how laser light is made, where I'm jumping around. But I kind of dropped that off. I can only do it so many times. I want to give myself traumatic brain injury. So how does laser light do damage? It does it in a few different ways. For one thing, you can burn things, photocoagulation. You can blow things up, photodisruption, formation of a local plasma. The energy gets focused into a tiny little area and you get like a plasma formation that blows things up. And then photoablation. And what I'm trying to show here is you put the energy into the covalent bonds that hold the tissue together, and you cause it to disrupt. So you cause the bonds that hold the tissue and or the society together to break. And so then the tissue just ablates. So photoablation is rupture of covalent bonds without burning it, without blowing it up. It just falls apart. So how do we burn things? With colored lasers. We can go from the blue-green to the infrared. Blue-green is absorbed by pretty much everything on the way through, anything that's not clear, RPE, xanthophyll, iris, hemoglobin. As you move into the infrared, then diode is absorbed only by pigment epithelial melanin. So with a diode laser, all of the damage to the retina is collateral damage from heating up, from cooking the pigment epithelium. And it doesn't matter, you can deliver it through the pupil, you can deliver it through the sclera. It cooks the same melanin and does the same thing. Whereas the blue-green has to go through the pupil. The blue-green is more likely to pick up and get absorbed by hemoglobin and such, so it can be problematic. The YAG laser is 1064, so it's in the infrared range. It's not visible, and these are the high-powered pulses that cause optical breakdown, plasma formation, mechanical disruption. So since absorption is not necessary, it can cut semi-transparent membranes like the posterior capsule and below little holes and things. And then it's the excimer that does the sublimation, the rupture of the covalent bonds. So that's why it can treat all eye layers, including clear cornea, because it's absorbed by the molecules within the cornea. It disrupts their covalent bonds and sublimates the tissue into nothing. And this was from the early days of experiments with excimer lasers. Roger Steiner, Carmen Puliafito showed this, something like this, when they were playing with excimers. And you see this plume of tissue that's been sublimated by the excimer. It was interesting to watch the change in thought, because at the time RK was the only surgery and for refractive surgery, and so the thought was to use the excimer to cut RK like slits into the eye, and nobody really thought about it just took a while to have a change of mindset to think about ablating the whole cornea instead. But you see why it's really important to have air blowing across the cornea when you do this ablation, because if this cloud is in the way and the next ablation comes in, you're going to get an irregular ablation and scattering of light and bad things. So finally, we're at presenting symptoms. And this is a short section, but it tries to put everything together that we've been thinking about all day, from fundamentals of light to how to refract, to what is astigmatism, to vertex distance, all that stuff, into actual symptoms of human patients who are suffering and who we're trying to help. So we will break it down as you see here. First, name a factor other than disease that can reduce measured visual acuity. So that would include, I know this is obvious, but you're on the optics section. So uncorrected ametropia, the patient needs a refraction. Now, one way to tell is to use a pinhole. So that may seem obvious for a patient who just comes in, but I sometimes use a pinhole after I've done my best refraction, because I don't always know I got the refraction right. And so if I only got them to 20/30 or something with a refraction, put up a pinhole. And if you get down to 20/20, then it's like something isn't right. Maybe you got irregular astigmatism, or maybe you just did your refraction wrong. Pupil size. The pupil can be too large. We talked about that, exposing aberrations within the eye. Or it could be too small, less than 2.5 millimeter. You begin to get diffraction from small pupil. And then decreased contrast. This is like the eye chart might be bad, or the monitor for the eye chart. Saw that the other day. Went into an exam room, and it's like the monitor was turned way down. I don't know what had happened. It was like, I hope nobody made any like surgery decisions based on this monitor. Age. Young patients, we don't expect them to be 20/20 until 5 or 6. Old patients, just without specific disease, but just with aging, can have reduction in visual acuity to less than 20/20. Monocular diplopia. What do we do about, how do we diagnose monocular diplopia first? Well, it's if you cover one eye, of course, and then we put up a pinhole. And the pinhole almost always, but not always, take away monocular diplopia. So the causes include just refractive error, a surface problem on the eyes, irregular astigmatism. I just saw a patient maybe a week or two ago, and I had done strabismus surgery on him, but now he had triple vision. And so, but it was 20/20 vision. And his cataract surgeon didn't want to operate on a 20/20 eye. He's like, oh, the cataract's not bad enough. But the patient was like, I'm seeing triple, I'm getting all this terrible glare. And he said glare, so I was expecting to see a posterior subcapsular cataract, but he didn't have one. But on the retinoscopic reflex, you could see he had this like one little anterior cortical cataract that had a 3-part shape to it. And so he had 3 exact different refractive domains within his pupil. And each one of those 3 domains had a different refraction, was causing triple vision. So I sent back a note to the cataract surgeon saying, I know he doesn't have PSC, and I know he's 20/20 plus, but he's miserable. Take out his lens. Surface problem. Sometimes I get to see patients for strabismus or for diplopia who have dry eyes. Irregular astigmatism, lenticular irregularity, cataract, we just talked about that. It's only rare that a retinal problem will cause monocular diplopia. That one probably won't respond to a pinhole when that is the case. New glasses are no good. So a patient comes into your office, you do an exam, everything goes fine, and then they're leaving and they say, oh, could you give me the updated glasses? And you're like, oh, gee, I didn't do a refraction, but I see that he's 20/15 in both eyes. So yes, I can give you an updated prescription. Let's see, what is the current prescription? And you write that down, you hand it to the patient, and then they come back 3 weeks later and said, yeah, the new refraction, it's not, something's wrong with it. My old glasses are much better. So how could that be? Like what happened? So first you want to compare the axis and the power and make sure that they were made correctly. Sometimes the base curve can change. So the way that you can check the base curves is you can use this lens clock, the Geneva lens clock, and you push it against the glasses and it will read out in radius or in assumed diopters the curvature of both the back and the front surface. And then you can also figure out if the astigmatic power was ground into the back surface as minus power or put onto the front surface as plus power. Again, highly unlikely, but it happens. More likely is the base curve change between the two glasses, and that would be not so hard to tell. These pins do scratch, so you don't want to like spin it on the glasses, because then you'll return the patient two glasses, their favorite ones and the new ones that they don't like, and they both have like circular scratches on both sides. And it's like, you're probably never going to do this, but I'm just telling you. Have I ever done this one? I think maybe once. But not like some of the other ones I've talked about. What about this? This one I see a lot. Prism. Look for prism. So it's not that uncommon that people get prism because they got like a little hypertrophy of 2, and so someone will give them 2 a vertical and either tell them or not tell them and they forget, or not tell them or tell them and then they forget. And so you wrote that out, but whoever read the glasses didn't notice that there was prism in there, and now the prism's gone, and they don't like their vision. So also, if the optical centers are off, then then you could have accidental prism. Trauma to glasses. I had a little girl who she popped the lenses out of her glasses, and Dad popped them right back in again, but he flipped them, and so the optical centers were like way off. She didn't mind. It actually gave her a little base out prism, which helped her strabismus. But remember the other patient who was had the vertical diplopia from injured glasses. We talked about astigmatic grinding and then the coatings in the tint. So there are a lot of things to think about if the new glasses are no good, even if it's the identical prescription. Look, we haven't even finished. There's another whole page. Check the bifocals, the segment height, the progressive design. The designs can vary quite a bit. And then the power of the bifocals. And then you do want to also check your refraction, consider a cycloplegic refraction. In all of these cases, even in adults, I've seen 50-year-olds who should know better, who are like over-minus and accommodating a lot and having trouble from that. Big changes in cylinder, rapid changes, cataract, all the things in the differential of bad things that can happen that can cause refraction to change. Remember the ciliary tumor. Poor vision after your refraction. I mentioned using a pinhole. We mentioned using a high-powered Jackson cross cylinder. Check your eye chart. I already mentioned that. This is one that can be overlooked. It's not optical, but patients with latent nystagmus, oops. If you cover one eye, the latent nystagmus comes out and the vision is going to go way down. So you recheck binocular first and then try to use just a frosted occluder or a high plus lens, and dry eye. Any of those things can contribute. So then we've got, we're getting close, last couple. Patients who have headaches and present with headaches and eye strain. So first of all, we want to look for aphoria or atropia. Again, we want to look for prism in the glasses that either was there before or that wasn't there. We actually published a series of, a case history of a patient who had prism in her over-the-counter reading glasses, and a huge workup for it, for this double vision, like ERG, like MRI, anything with 3 letters was done, and any test with 3 letters. And it turned out that her over-the-counter reading glasses had vertical prism in them because they weren't made right. And so we looked and found that like 30% of over-the-counter reading glasses had either like some vertical prism or weren't made to spec or had giant pupillary distances. So cycloplegic refraction, look for latent hyperopia. That could certainly cause headaches. So can overcorrection. So just don't underestimate that cycloplegic refraction can help you in some of these patients. And early presbyopia, it's not that uncommon, especially if there's already latent hyperopia. Oops. Yes, our friend, Dr. Glaucom Flecken, not my friend, but a lot of us follow him and his work. 45-year-old patient was taking huge doses of non-steroidals for 3 weeks due to headaches. Turns out she just needed reading glasses. Given that she would have developed a gastric ulcer, which would have perforated, leading to sepsis and death, the lesson, as always, is that reading glasses save lives. Thank you, doctor. And that is why we are here, to save lives. We can diagnose tumors from refractive shifts. We can keep people from cutting their fingers off because of their bifocal design. And now we can give them reading glasses for their headaches. So we have reviewed our formulas, prescribing glasses, instruments, presenting symptoms. I somehow babbled on for long enough to go probably the longest I've ever done with this, especially with just 5-minute breaks. So I hope, I don't know, we'll see. The 2020 version was at 25,000 views last I saw. So maybe that'll still be the best one, we'll see. But I try to keep you awake, help you get ready. I mean, yes, you've got this test coming up, but it isn't, in my view, it isn't about the test really. I mean, yes, it is about the test for you right now because you need to get through that. But I want to help you. And it isn't even about being a better doctor, but I also want that too. But it's so you can like enjoy your life and your career and feel like you have some ownership over what you're doing when you're taking care of patients, and to be involved and to be thoughtful and to be innovative. And if you understand how stuff works, you understand how it doesn't work. So then you can think up new things and, you know, be the next gold strand and figure out the second generation slit lamp that'll be used for all time. So none of that happens without having some understanding of what you're doing. But you don't get the understanding if you don't study it, but you don't study it if it's too boring. So I really appreciate everybody's support and comments, and best of luck if you do have a test coming up. And we'll finish with this Songs for Teaching song that just hits it right on the nose. Thank you very much.
I see the light in all the colors of the rainbow.